Welcome to Endless Universe, where the cosmos unfolds its mysteries to calm your mind and spark quiet wonder. I'm your guide here to weave a story that carries you through the vastness of space, gently probing one of humanity's deepest questions: what lies beyond the edge of the universe? A few nights ago I stood on my porch in the cool autumn air, a cup of coffee warming my hands, staring at a sky so clear the stars seemed to hum. The Milky Way stretched above a faint ribbon of light, and I found myself wondering, where does it all end? Is there a boundary out there, or does the universe simply go on like a song without a final note? This question is our companion tonight, a soft thread to follow as we begin our journey. Where are you watching from, and what time is it in your corner of the cosmos? If this tale speaks to you, please give it a like, maybe subscribe, and let's wander the stars together. I hope it's just intriguing enough to soothe, not stir your thoughts. The universe, as cosmologists define it, is the entirety of space-time, matter and energy, a vast manuscript written over 13.8 billion years. To speak of its edge is to grapple with a concept that feels both intuitive and elusive, like trying to pinpoint the end of a horizon. In astronomy, we often refer to the observable universe, a sphere roughly 93 billion light-years across, bounded by the cosmic light horizon. This horizon marks the farthest distance light has travelled, since the universe's birth, a limit not of space but of time. Beyond it there may be more galaxies, more stars, or perhaps something entirely different, a void, a curve, or realms we can't yet imagine. The question isn't just scientific. It's a spark that has ignited human curiosity for centuries, from stargazers in ancient Greece to astronomers peering through modern telescopes. Let's step back to a pivotal moment in 1929 when Edwin Hubble, an American astronomer, stood at the Mount Wilson Observatory in California. His observations of distant galaxies revealed a cosmological redshift, a stretching of light that showed the universe is expanding, its contents drifting apart like leaves on a widening river. This discovery, which we'll explore further, hinted that the universe has no fixed edge, no wall to bump against. Yet it also deepened the mystery: if the universe is growing, what lies outside its current expanse? Hubble's work built on earlier ideas like those of Belgian priest Georges Lemaître, who envisioned a cosmos born from a primordial atom. Their insights are threads in our story, stitching the past to the present as we seek answers. This question resonates in American culture, where the unknown has always beckoned. Think of the Apollo missions, when astronauts like Neil Armstrong looked back at Earth from the moon, a fragile blue marble in the cosmic sea. Or consider Carl Sagan's Cosmos, a television series that invited millions to ponder their place in the universe. Even in everyday moments, lying on a blanket at a national park counting shooting stars, the idea of an edge feels personal. The elements in your body, forged in ancient stars, tie you to this cosmic narrative. You're not just an observer. You're part of the story, your existence, a chapter written in stardust. As we begin, the science offers clues, but no certainties. The cosmic microwave background, a faint glow discovered in 1965 by American scientists Arno Penzias and Robert Wilson, marks the universe's infancy, a snapshot from 380,000 years after its birth. It's a boundary of sorts, but not the edge we seek. Einstein's general relativity suggests the universe's shape, flat, curved, or infinite, holds the key a puzzle will unravel as our tale unfolds. For now, let's hold the question lightly, like a book we've just opened its pages, promising wonder. The cosmos is vast, but tonight it's a quiet friend inviting you to listen as the story continues. What does it mean for something to begin, not just a day or a journey, but the entirety of existence, space-time, and all that fills it? As we continue our quiet exploration of what lies beyond the universe's edge, we're drawn to a moment 13.8 billion years ago, when the cosmos itself was born. This event, known as the Big Bang, wasn't a burst like a firecracker in the night, but a profound unfurling, a primordial singularity, expanding to create the universe we know. From the cosmic light horizon we gazed at last time, we now step back to the dawn of everything, asking if the universe had a beginning. Could it also have an end, a boundary where its story stops? Let's trace this origin gently, letting the tale unfold like a scroll in a silent library. The Big Bang began with a singularity, a point of infinite density and temperature, smaller than a proton, containing all the matter and energy of the cosmos. In an instant it expanded, not into pre-existing space, but creating space itself. This wasn't a slow bloom but a rapid surge driven by a phase called cosmic inflation, theorized by Russian physicist Alexei Starobinsky, and later refined by others. In less than a trillionth of a second, the universe grew exponentially, smoothing out its structure like a sheet stretched taut. As it cooled, the first particles formed in a process called nucleosynthesis, forging hydrogen and helium, the seeds of stars. This cosmic dawn, a mere few minutes long, set the stage for galaxies, planets, and the very elements that make up your breath, your bones, your world. The idea of the Big Bang took shape through the work of a Belgian priest and mathematician Georges Lemaitre, who in 1927 proposed that the universe began as a primeval atom. His vision, initially met with skepticism, found support. When astronomers observed the universe's expansion, a discovery we'll explore further. By 1948, Russian-American physicist George Gamow predicted that the Big Bang would leave a faint glow, the cosmic microwave background CMB. This prediction came to life in 1965 when two scientists in New Jersey detected a persistent radio hiss, a relic of the universe's infancy. The CMB, mapped by satellites like Europe's Planck mission, is a snapshot of the cosmos at 380,000 years old, a testament to its fiery birth and a clue to its boundaries. This story of creation echoes across cultures far beyond the laboratories of Europe and America. In Hindu mythology, the universe emerges from a cosmic egg Brahmanda splitting to birth, time and space, a parallel to the singularity's expansion. Among the Dogon people of Mali star lore describes a universe born from a primal vibration, a concept that resonates with the Big Bang's sudden onset. These narratives, though distinct, share a human instinct to seek origins, to find meaning in the cosmos. For you perhaps sitting in a quiet room with a window open to the night, this idea might feel closer still. The carbon in your coffee cup, the oxygen in the air, these were forged in that primordial fire, tying you to the universe's first moments. The Big Bang reshapes our question about the edge. If the universe began everywhere at once, there's no central point to anchor a boundary. Unlike a balloon expanding into a room, the cosmos expands within itself, a process called metric expansion. If infinite, it has no edge. If finite, it might curve back like a sphere's surface. This puzzle, rooted in the work of Indian mathematician Subrahmanyan Chandrasekhar, who studied stellar evolution, challenges us to rethink beyond. The universe's dawn offers no clear map, but it invites us to wonder, to let the question linger, like the afterglow of a distant star. Consider a moment when you've watched a sunrise, the world shifting from shadow to light. That transition, fleeting yet eternal, mirrors the Big Bang, a moment when nothingness became everything. This isn't just science. It's a story that binds us to the cosmos, from ancient myths to modern telescopes. As you rest tonight, let this tale of creation be a quiet thread weaving through your thoughts, carrying you deeper into the vastness of our shared journey. Across the ages, humans have looked to the night sky, weaving stories to make sense of its boundless depths. In ancient Sumer, scribes etched tales of gods shaping the heavens on clay tablets. In Polynesian lore, navigators saw the stars as guides across vast oceans. This urge to understand the cosmos, to trace its limits, binds us to the question we're exploring: what lies beyond the universe's edge? From the cosmic light horizon and the primordial singularity of the Big Bang, our story now turns to a revelation that reshaped our view of existence. The universe is not a fixed tapestry, but a living one, unfurling through time, its galaxies drifting apart in a process called metric expansion. This cosmic motion, discovered a century ago, deepens our quest, suggesting that the edge we seek may not be a place, but a mystery woven into the fabric of space itself. The science of expansion began with a quiet observation in 1912, when American astronomer Vesto Slipher, peering through a telescope in Arizona, noticed that the light from distant galaxies was stretched, a phenomenon known as cosmological redshift. This redshift, akin to the deepening pitch of a receding train's whistle, hinted that galaxies were moving away. By 1929, Belgian astronomer Georges Lemaitre and others built on this, proposing that the universe itself was growing. The decisive moment came when Edwin Hubble, using California's Mount Wilson telescope, quantified this motion, showing that galaxies recede faster the farther they are, a relationship now called Hubble's law. The Hubble constant, a measure of this expansion rate, revealed a cosmos stretching uniformly, like a scroll unrolling in every direction, carrying stars and galaxies along with it. This discovery upended centuries of thought. For millennia, scholars like Ptolemy in ancient Egypt imagined a static cosmos with Earth at its centre. The idea of an expanding universe was as revolutionary as the heliocentric model of Copernicus. In the 1930s, Indian physicist Subrahmanyan Chandrasekhar's work on stellar dynamics helped refine our understanding of how gravity interacts with this expansion, shaping the cosmos's evolution. The scale factor, a mathematical term describing how distances in the universe grow, became a cornerstone of cosmology. Unlike a balloon inflating into a room, the universe expands within itself with no external space required. This means the cosmic light horizon we explored isn't a physical edge, but a limit of visibility beyond which the universe may continue unseen, stretching our imagination. The story of expansion resonates across cultures, echoing humanity's drive to explore the unknown. In Yoruba, mythology from West Africa, the deity Obatala shapes the world from a vast void, a narrative of creation through growth that parallels cosmic expansion. In Chinese philosophy, the concept of qi, a dynamic flowing energy, mirrors the universe's restless motion. These ideas, though ancient, capture the same curiosity that drove astronomers to chart the cosmos. For you perhaps, gazing at the stars from a city balcony or a rural field, this expansion feels personal. The night sky with its scattering of light is a canvas of motion, each star a marker in a universe that's been growing since its fiery birth. The practical echoes of this discovery touch our lives in subtle ways. The Hubble constant, refined by missions like Japan's Akari satellite, helps us date the universe and map its history. Technologies like satellite navigation, which rely on general relativity to account for space's stretching, owe a debt to this science. More deeply, the elements in your body, hydrogen from the Big Bang, carbon from ancient stars, were carried across the cosmos by this expansion. It's a quiet connection, one that makes a moment of stargazing feel like reading a page from the universe's own story written over billions of years. As you settle into this evening perhaps, with the soft hum of the world around you, the idea of an expanding universe offers a gentle rhythm. It's a reminder that the cosmos is alive, its boundaries shifting, its mysteries unfolding. The question of what lies beyond an edge, a void, or something stranger grows richer with each step, a thread in the tale we're weaving together. In the early 1920s, a Russian mathematician named Alexander Friedmann sat in a dimly lit study in Petrograd, his desk strewn with papers and equations. The world outside was turbulent, but Friedmann's mind was fixed on a grander puzzle, the shape of the universe itself. Building on Einstein's general relativity, he proposed that the cosmos could take one of three forms: flat, curved like a sphere, or open like a saddle each, with profound implications for its boundaries. As we continue our journey from the cosmic light horizon, the primordial singularity, and the universe's expansion, we now explore this space-time topology, a concept that shapes our quest to understand what lies beyond the universe's edge. Is the cosmos infinite, or does it fold back on itself, a finite enigma with no end? Let's wander this question, letting it guide us like a compass through the quiet night. The geometry of the universe is no mere abstraction. It's a framework that determines whether an edge exists at all. Einstein's 1915 theory of relativity revealed that space and time are a malleable fabric warped by matter and energy. Friedmann's Friedmann equations, derived in 1922, showed that the universe's shape depends on its density described by the omega parameter. If omega equals 1, the universe is flat, its geometry like an infinite plane, where parallel lines never meet. If greater than 1, it's closed a finite sphere where space curves back like the surface of a globe. If less than 1, it's open an infinite saddle, where space stretches outward. Each scenario reshapes our question. A flat or open universe suggests no edge, only endless expanse. A closed one implies a finite cosmos, yet still boundless, with no beyond to find. The quest to measure this geometry has been a global endeavour. In the 2000s, the Wilkinson Microwave Anisotropy Probe WMAP, led by an international team, studied the cosmic microwave background, the relic glow from the Big Bang we've discussed. By analysing tiny temperature variations like ripples in a cosmic sea, WMAP found the universe is flat to within 0.4%, a result refined by Europe's Planck satellite in 2013. This flatness, a delicate balance of matter and energy, suggests an infinite cosmos, but the margin of error leaves room for doubt. Could a slight curvature hide like a subtle arc in a vast landscape? This uncertainty keeps the mystery alive, a thread in our story that binds science to wonder. Humanity has long grappled with the shape of existence. In ancient India, Jain cosmology described a universe with finite layers, stacked like a cosmic tower, yet boundless in its complexity. In Norse mythology, the world is a flat disk encircled by a serpent, a vision of containment that contrasts with infinity. These ideas, though symbolic, reflect the same curiosity that drove Friedman's equations. For you, perhaps sipping tea on a quiet evening, this question might stir a memory of a childhood puzzle where the pieces never quite fit. The universe's shape is such a puzzle, its solution written in the stars, connecting a moment of reflection to the grandest scales. The science of geometry touches our lives in unexpected ways. The flatness of the universe informs models of its fate, guiding missions like Japan's Light Bird, set to probe the cosmos's early moments. Technologies like GPS, which rely on relativity to navigate spacetime's subtle curves, owe a debt to this work. More deeply, the atoms in your hand, forged in the Big Bang and shaped by expansion, are part of this geometric dance. As you sit with this thought, the universe's shape becomes more than a concept. It's a story, one that invites you to pause, to breathe, to let the vastness of eternity settle like a soft shadow across your mind. When you look at a star, you're not seeing it as it is now, but as it was its light, a messenger from the past, travelling across eons to reach your eyes. This simple truth lies at the heart of our journey, from the cosmic light horizon, the primordial singularity, the universe's expansion, and its geometric form. In cosmology, we call the farthest light we can see the observable universe a sphere stretching 93 billion light-years across, bounded by the cosmic light horizon. This isn't a physical edge, but a limit set by time and the speed of light, a veil beyond which our gaze cannot pierce. As we probe what lies beyond the universe's edge, this horizon becomes our guide, a boundary that shapes our understanding of the cosmos and its mysteries. Let's explore this softly, letting the light of ancient stars lead us through the quiet of the night. The observable universe is defined by light travel time, the duration it takes for light to reach us, since the Big Bang 13.8 billion years ago. Because the universe is expanding as we learn, the farthest objects are now much farther than 13.8 billion light-years away, a distance cosmologists measure as the come-moving distance roughly 46.5 billion light-years to the horizon. This boundary, sometimes called the particle horizon, marks the edge of what we can observe, not because space ends, but because light from beyond hasn't had time to arrive. It's as if the universe is a vast gallery, its farthest walls lit by the oldest light, while the rooms beyond remain in shadow. What lies there, more galaxies avoid, or something stranger, depends on the universe's shape and size, questions we've begun to unravel. The history of this concept is a tale of persistence. In the 1960s, Australian astronomer John Bolton helped pioneer radio astronomy, detecting signals that hinted at the universe's vast scale. The discovery of the cosmic microwave background CMB, the faint glow from the Big Bang's aftermath, gave us a clearer view. Found by American scientists Arno Penzias and Robert Wilson in 1965, the CMB marks the moment when the universe cooled enough for light to travel freely, 3,000 years after its birth. Missions like Europe's Planck satellite mapped this glow, revealing the observable universe's limits. These efforts spanning continents show how our understanding of the horizon has grown like a map drawn by countless hands over decades. Across cultures, the idea of a cosmic limit resonates deeply. In Aboriginal Australian traditions, the Dreamtime stories describe a sky world, where ancestors shaped the stars, a realm just beyond human reach. In Japanese Shinto beliefs, the heavens are a sacred expanse, their boundaries blurred by the divine. These perspectives, like our scientific horizon, reflect a yearning to touch the untouchable. For you, perhaps lying back in a lawn chair under a starry sky, this idea might feel closer. The stars you see are a snapshot of the past, their light a bridge between now and then, tying your quiet moment to the universe's grand history. The horizon's implications reach into our lives. The observable universe informs astronomy, guiding telescopes like Chile's Atacama, large millimeter array to probe distant galaxies. Technologies like satellite navigation, reliant on relativity to account for light's journey, owe a debt to this science. More personally, the night sky you gaze at is a window to the observable cosmos, its farthest reaches marked by the CMB's ancient light. As you hold this thought, the horizon becomes more than a limit. It's a reminder of our place in a vast story, one that stretches beyond sight, inviting you to rest in its gentle mystery. Could there be other universes, each with its own stars, galaxies, and laws of nature existing just beyond our reach? This question stretches the boundaries of our journey, from the cosmic light horizon, the primordial singularity, the universe's expansion, its geometric form, and the limits of what we can see. In cosmology, the multiverse hypothesis proposes that our universe is but one of many a single page in a cosmic anthology, where each page tells a different story. As we seek what lies beyond the universe's edge, the idea of a multiverse offers a bold possibility. Perhaps beyond is not a void or a boundary, but a tapestry of other realms, each as vast as our own. Let's explore this idea gently, letting it unfold like a whisper from the cosmos, guiding us through the stillness of the night. The multiverse hypothesis emerges from the science of cosmic inflation, the rapid expansion that followed the Big Bang, which we touched on earlier. In the 1980s, Russian physicist Andrei Lindy proposed a model called eternal inflation, suggesting that inflation didn't stop uniformly. Instead, pockets of space continue to inflate, forming bubble universes, distinct regions, with their own physical constants and histories. Our universe, with its familiar laws of physics, might be one such bubble floating in a vast multiverse where other bubbles have different rules, perhaps where gravity repels or time flows backward. This idea, while speculative, addresses our central question. If our universe has an edge, the multiverse might be what lies beyond a collection of realities we cannot see or touch. The roots of this concept trace back to earlier thinkers. In 1957, British physicist Hugh Everett proposed the many worlds interpretation of quantum mechanics, suggesting that every quantum event spawns parallel realities. Though distinct from cosmological multiverses, Everett's work sparked debate about multiple realms. By the 1990s, South African cosmologist Neil Turok and others linked inflation to multiverse theories building on Lindy's ideas. These efforts spanning continents show how the multiverse remains a frontier unproven, but grounded in rigorous mathematics. It's a hypothesis that pushes the limits of science like a telescope, aimed at a horizon we can only imagine, yet it draws from the same curiosity that mapped the cosmic microwave background. Cultures worldwide have long speculated about other worlds. In South Asian Jainism, the cosmos is a series of layered realms, each with its own beings and cycles, a vision that echoes the multiverse's multiplicity. Among the Zulu of Southern Africa, oral traditions describe parallel worlds where ancestors dwell, a concept of coexisting realities. These stories, like modern cosmology, grapple with the idea of beyond reflecting humanity's instinct to imagine more than what we see. For you, perhaps sitting by a window with the night sky framed in glass, this idea might stir a sense of possibility, like flipping through a book of stories, each one a universe unto itself. The multiverse, though theoretical, touches our lives indirectly. It inspires questions about our universe's uniqueness, guiding research, like Europe's Euclid mission, which studies cosmic expansion to test inflationary models. In everyday moments, the idea of other realms might resonate when you ponder. What if a mischance, a different path? The multiverse is a cosmic version of that question, a reminder that our reality is one of many possibilities. As you rest with this thought, the notion of other universes becomes a quiet invitation not to solve the mystery, but to let it linger, a soft echo in the vastness of the night. In the ancient city of Babylon, under a sky thick with stars, priests climbed ziggurats to chart the heavens, believing the cosmos was a dome cradling the earth, its edges guarded by divine forces. Across oceans and centuries, the Maori of New Zealand wove tales of Ranginui the Sky Father, whose separation from the Earth Mother marked the universe's birth, its boundaries vast yet unseen. These mythopoeic visions, etched in clay and song, are threads in our journey, connecting the cosmic light horizon, the primordial singularity, the universe's expansion, its geometry, and the possibility of a multiverse. As we seek what lies beyond the universe's edge, these ancient stories offer a timeless perspective, framing the cosmos as both infinite and contained a paradox that echoes modern science. Let's trace these tales, letting their wisdom guide us like lanterns in the quiet dusk. Long before telescopes, humans imagined the universe's cosmological boundary through narrative. In Mesopotamia, the Enuma Elish epic described a cosmos born from chaos, its edges divine frontier where gods held sway. In ancient China, Taoist texts spoke of the Tai Chi, a boundless void giving rise to all existence with no clear edge but an eternal flow. These stories weren't mere folklore. They were early attempts to grapple with the same question we ask today. The Greek philosopher Anaximander in the 6th century BCE proposed an apeiron, an infinite boundless source of all things, foreshadowing modern ideas of an infinite universe. These ancient cosmologies, though unscientific by today's standards, laid the groundwork for our quest, their questions as vital as those posed by the Friedmann equations or the cosmic microwave background. Science has built on these foundations, refining our view of the cosmos's limits. The Babylonians' domed sky finds a distant echo in the closed universe model, where space curves back on itself, finite yet edgeless, as we explored in our discussion of geometry. The Taoist boundless void aligns with a flat universe scenario stretching infinitely without a border. In the 17th century, German astronomer Johannes Kepler, blending mysticism and mathematics, imagined a universe with no center or edge, a vision that resonates with the metric expansion we've discussed. These connections show how ancient tales inform modern cosmology, bridging the gap between myth and measurement, like a conversation across millennia. The cultural significance of these stories runs deep. In African Akan traditions, the sky god Nyami oversees a cosmos with unseen boundaries, a realm of mystery that mirrors our own search for the universe's edge. In Nordic sagas, the world tree Yggdrasil links realms beyond mortal reach, a poetic multiverse, not unlike the bubble universes we pondered. These narratives, diverse yet universal, reflect humanity's need to define the infinite. For you, perhaps glancing at the stars through a bedroom window, these tales might recall a moment of wonder, a campfire story, a book of myths where the unknown felt both vast and intimate, a feeling that ties you to ancestors who gazed at the same sky. These ancient visions have a quiet presence in our lives. The impulse to map the cosmos seen in Babylonian star charts lives on in telescopes like South Africa's Meerkat, probing the universe's depths. The elements in your body, forged in the Big Bang and scattered by expansion, connect you to the creation myths of old, where gods and stars alike shaped existence. As you rest tonight, the stories of the infinite become a soft bridge, linking the past to the present, carrying you deeper into the cosmic narrative we're weaving, where the question of what lies beyond remains a gentle, unanswered call. What is nothing? Not the absence of clutter in a room or the quiet of a late evening, but true ontological nothingness, a state devoid of space-time or existence itself. As our journey weaves through the cosmic light horizon, the primordial singularity, the universe's expansion, its geometry, the observable limits, the multiverse and ancient tales. We now pause to ponder this profound question. If the universe has an edge, what lies beyond? Is it a void? A silence so complete it defies comprehension, or something our minds cannot grasp? This idea of nothingness, explored by philosophers and scientists alike, shapes our quest to understand what lies past the cosmological boundary. Let's delve into this mystery, letting its quiet weight settle like a shadow cast by distant stars. In philosophy, nothingness has long been a puzzle. In the 17th century, German philosopher Gottfried Leibniz asked why there is something rather than nothing, a question that echoes in our search for the universe's edge. If our cosmos, born in the Big Bang, unfurling through expansion shaped by geometry, is finite what surrounds it, an ontological void offers one answer, a state with no properties, no dimensions, no time. Yet modern science complicates this. The quantum vacuum, far from empty, teems with fleeting particles as described by German physicist Werner Heisenberg's uncertainty principle. This suggests that even nothing is alive, with potential a restless sea of energy that challenges the very concept of absence. The history of this idea spans continents. In the 5th century BCE, Chinese philosopher Laozi, in the Tao Te Ching, described the Tao as a formless void from which all things arise, a vision of nothingness as creative rather than barren. In the 20th century, British philosopher Bertrand Russell grappled with the same question, arguing that nothingness might be a logical impossibility. These debates find echoes in cosmology. The multiverse hypothesis we explored suggests that beyond our universe lie other realms, not a void, but a tapestry of realities. Yet if no multiverse exists, the alternative might be a vacuum state, not empty, but a minimal framework of quantum fluctuations, a concept rooted in the work of Japanese physicist Hideki Yukawa. Cultures across the globe have wrestled with nothingness. In Buddhist traditions from India, shunyata, emptiness, is not a desolate void, but a state of infinite possibility, a perspective that mirrors the quantum vacuum's potential. Among the San people of southern Africa, stories of the first creation describe a formless expanse before the stars and nothingness that birthed light. These ideas resonate with our own curiosity, whether you're sitting in a quiet study or gazing at the night sky. The concept of nothing feels personal, like the silence after a conversation fades, a moment that invites reflection on what it means to exist. Science and philosophy converge in everyday life. The quantum vacuum informs research at facilities like Switzerland's CERN, probing the nature of empty space. The elements in your body, born in the Big Bang and shaped by expansion, remind you that even nothing is part of your story. As you rest tonight, the idea of nothingness becomes a quiet companion, not a puzzle to unravel, but a space to breathe, a silence that holds the weight of the cosmos's mysteries in its gentle embrace. What is nothing? Not the quiet of an empty room or the pause between breaths, but a profound absence, ontological nothingness, a state without space-time or existence itself. Our journey, tracing the cosmic light horizon, the primordial singularity, the universe's expansion, its geometry, the observable limits, the multiverse and ancient tales, now turns to this elusive concept. If the universe has an edge as we've pondered what lies beyond, is it a void so complete it defies thought, or something stranger woven into the fabric of reality? Philosophers and scientists, from ancient sages to modern theorists, have wrestled with this question, shaping our quest to understand the cosmological boundary. Let's explore this mystery gently, letting its weight settle like the hush of a starless night, guiding us deeper into the cosmic narrative. In philosophy, nothingness is a paradox. In 1714, German philosopher Gottfried Leibniz posed a question that still resonates: why is there something rather than nothing? If our universe, born in the Big Bang and stretched by metric expansion, is finite, what surrounds it? An ontological void suggests a state with no properties, no dimensions, no time, no matter. Yet modern physics challenges this simplicity. The quantum vacuum, far from empty, is a restless sea of vacuum fluctuations, where particles flicker in and out of existence, as described by German physicist Werner Heisenberg's uncertainty principle in 1927. This suggests that nothing is not barren but alive with potential, a concept that complicates our search for what lies beyond the universe's edge, whether it's a void or a multiverse of bubble universes. This idea has deep historical roots. In the 5th century BCE, Chinese philosopher Laozi in the Tao Te Ching described the Tao as a formless void, the source of all existence, a nothingness that births everything. In the 20th century, British philosopher Bertrand Russell argued that nothingness might be a logical impossibility, as existence itself implies something. These debates find echoes in cosmology. The multiverse hypothesis we explored suggests that beyond our universe lie other realms, not a void, but a tapestry of realities. If no multiverse exists, the alternative might be a vacuum state, a minimal framework of quantum energy, as proposed by Japanese physicist Hideki Yukawa in the 1930s. This interplay of philosophy and science, spanning cultures and centuries, frames nothingness as both absence and potential, a duality that enriches our quest. Cultures worldwide have grappled with this concept. In Indian Buddhist traditions, shunyata, emptiness, is not desolation, but a state of infinite possibility, a perspective that mirrors the quantum vacuum's dynamic nature. Among the San people of southern Africa, creation stories describe a formless expanse before the stars, a nothingness that gave rise to light, echoing the primordial singularity. In ancient Greece, philosopher Parmenides argued that nothing cannot exist, as thought itself implies being. These narratives, diverse yet universal, reflect humanity's struggle to define the indefinable. For you perhaps, sitting in a quiet corner with the night sky beyond your window, nothingness might feel personal, a moment of silence after a busy day, a space where thoughts drift toward the infinite. Science offers a bridge between these ideas and our daily lives. The quantum vacuum informs experiments at facilities like Switzerland's CERN, where physicists probe the nature of empty space, seeking clues to the universe's boundaries. The cosmic microwave background, a relic of the Big Bang, marks the edge of our observable universe, but beyond it, the quantum vacuum might extend a restless nothing that defies emptiness. The elements in your body, carbon, oxygen, forged in the Big Bang and scattered by expansion, are part of this story, connecting you to the cosmos's origins. Even technologies like medical imaging, rooted in quantum mechanics, owe a debt to our understanding of the vacuum state, tying the abstract to the tangible. The philosophical weight of nothingness invites introspection. Imagine a moment when you've stared into a starless sky, the darkness heavy with possibility. That feeling, both humbling and expansive, mirrors the question of what lies beyond. If the universe is finite as its space-time topology might suggest, nothingness could be a boundary, a silence beyond comprehension. If infinite or part of a multiverse, the beyond might be a chorus of other realities, each with its own laws. The work of Indian philosopher Nagarjuna, who saw emptiness as the root of existence, aligns with modern cosmology's view of a dynamic void. This interplay of ideas from ancient texts to particle accelerators weaves a narrative that's both vast and intimate. As you rest tonight, the concept of nothingness becomes a quiet thread in our cosmic tale. It's not a void to fear, but a mystery to hold, like the pause before a melody begins. The universe with its galaxies, stars, and unseen realms may end in silence or stretch into infinity, but for now let this question linger, a gentle whisper that carries you deeper into the story we're telling, where the cosmos's edges remain just out of sight. At the smallest scales of existence, where particles flicker like shadows and reality blurs the universe, reveals a hidden layer, the quantum realm. Our journey weaving through the cosmic light horizon, the primordial singularity, the universe's expansion, its geometry. The observable limits, the multiverse, ancient tales, and the concept of nothingness now turns to this microscopic frontier. Quantum mechanics, with its quantum fluctuations and Heisenberg uncertainty, offers a lens to probe the cosmological boundary we seek. Could the edge of the universe, the question of what lies beyond, be shaped by the strange laws of the subatomic world? Perhaps the beyond is not a void or another realm, but a veil woven at the Planck scale where space and time themselves dissolve. Let's explore this gently, letting the quantum world guide us like a faint glow in the cosmic dusk. Quantum mechanics governs the behavior of particles smaller than atoms, where rules like Heisenberg's uncertainty principle dictate that nothing is fixed position and momentum dance in a probabilistic haze. In cosmology, this principle applies to the quantum vacuum, a state we encountered when pondering nothingness, where fleeting particles emerge and vanish. German physicist Max Planck in 1900 introduced the Planck scale, a realm where space-time becomes granular, defying classical notions of continuity. At this scale, about 10 around 35 meters, the universe's edge might not be a sharp boundary, but a fuzzy frontier where quantum effects blur the distinction between inside and beyond. If the universe is finite as its space-time topology might suggest, the quantum veil could mark its limit, a place where existence itself becomes uncertain. The history of quantum cosmology is a global tapestry. In the 1920s, Indian physicist Satyendra Nath Bose collaborated with Einstein to describe particles now called bosons, laying the groundwork for quantum field theory. By the 1980s, British physicist Stephen Hawking applied quantum mechanics to cosmology, proposing that quantum fluctuations in the early universe during cosmic inflation seeded the formation of galaxies. These fluctuations, stretched by expansion, are visible in the cosmic microwave background linking the quantum realm to the observable universe. Hawking's work suggests that the universe's boundaries, if they exist, might be defined by quantum processes, a concept explored by Russian theorist Vyacheslav Mukhanov. This interplay of scales, microscopic to cosmic, reshapes our questions, suggesting the beyond might be a quantum tapestry, not a simple void. Cultures have long intuited this connection between the small and the vast. In Tibetan Buddhism, the concept of dependent origination suggests all things arise from interconnected causes, a parallel to quantum entanglement, where particles are linked across vast distances. Among the Aboriginal peoples of Australia, stories of the Dreamtime describe a world woven from invisible threads, echoing the quantum web of probabilities. These perspectives, like modern physics, see the cosmos as a unity of scales. For you, perhaps pausing in a quiet moment, this idea might resonate, a sense that the smallest details, like the flicker of a candle, connect to the grandest questions, tying your thoughts to the stars. The quantum realm touches our lives in practical ways. Technologies like MRI scanners rooted in quantum principles rely on the same physics that probes the universe's edge. Research at Japan's Kamioka Observatory studying quantum neutrinos seeks clues to the cosmos's origins. The elements in your body, shaped by nucleosynthesis and scattered by expansion, were influenced by quantum processes in the Big Bang. As you rest tonight, the quantum veil becomes a subtle thread in our cosmic story, not a barrier but a mystery, inviting you to ponder the unseen with a quiet sense of wonder. In 1998, two teams of astronomers, one led by Australian physicist Brian Schmidt in Canberra, the other by American Saul Perlmutter in California, gathered data that would jolt the world of cosmology. Observing distant supernovae, they expected to find the universe's expansion, which we've traced from the primordial singularity through its metric expansion and space-time topology, slowing under gravity's pull. Instead, they discovered something startling. The expansion was accelerating, driven by a mysterious force dubbed dark energy. This revelation, like a new chapter in our cosmic story, reshapes our quest to understand what lies beyond the universe's edge. Could dark energy, this unseen pulse, hold clues to the cosmological boundary pushing the cosmos ever outward? Let's explore this force, gently letting its mystery flow like a quiet current through the night. Dark energy is a term for an unknown form of energy that permeates all of space, driving the accelerated expansion of the universe. It's not a substance you can touch, but a property of space itself, contributing roughly 68% of the universe's total energy, according to measurements from Europe's Planck satellite. In Einstein's general relativity, dark energy is often modelled as a cosmological constant or lambda term, a concept Einstein introduced in 1917 to stabilise his equations, only to later call it his greatest blunder. The 1998 supernova observations revived this idea, showing that dark energy counteracts gravity, pushing galaxies apart faster over time. Unlike the quantum vacuum fluctuations we explored, dark energy operates on cosmic scales, shaping the universe's fate and its potential boundaries. The discovery of dark energy was a global effort. Australian astronomer Robert Kirshner, a mentor to Schmidt, laid groundwork by studying supernovae as cosmic distance markers. Meanwhile, Canadian physicist Wendy Friedman's work on the Hubble constant helped calibrate these measurements. By analysing Type Ia supernovae stellar explosions with consistent brightness, the teams found that distant galaxies were receding faster than expected, a finding confirmed by South Africa's Southern African Large Telescope. This accelerated expansion suggests that the universe, whether flat or curved as we discussed, may grow forever, stretching the cosmic light horizon farther from our reach. If there's an edge, dark energy might define its ever-receding nature, a boundary that slips away like a horizon at sea. Cultures across history have sensed such unseen forces. In ancient Egyptian cosmology, the god Nun represented a chaotic, formless energy, sustaining the cosmos, a distant echo of dark energy's pervasive influence. In Hindu philosophy, prana, a life force permeating the universe, parallels the idea of an energy shaping existence. These concepts, though symbolic, reflect humanity's intuition of a dynamic cosmos, much like the multiverse or shunyata we've pondered. For you, perhaps watching the stars from a porch swing, dark energy might evoke a sense of motion, like the wind rustling leaves, unseen yet undeniable, connecting your quiet moment to the universe's vast pulse. Dark energy's impact extends to our lives. It informs missions like Japan's EXORISM telescope, probing the cosmos' structure to refine our understanding of the scale factor. Technologies like GPS, reliant on relativity to account for space's expansion, owe a debt to this science. The atoms in your body, forged in the Big Bang and scattered by expansion, are shaped by the same cosmic forces dark energy drives. As you rest tonight, dark energy becomes a subtle rhythm in our story, a force that pushes the universe outward, carrying our question what lies beyond into the gentle expanse of the cosmos. In the myths of the Inca, the creator god Viracocha shaped the cosmos from a primordial void, leaving behind a faint light to mark its birth. Across the world, the Hausa people of northern Nigeria tell of a sky filled with ancestral spirits, their glow a reminder of creation's dawn. These stories passed down through generations echo a scientific truth we've woven into our journey, from the cosmic light horizon to the primordial singularity. The universe's expansion, its geometry, observable limits, multiverse possibilities, ancient tales, the concept of nothingness, quantum realms, and the pulse of dark energy. Today we turn to a relic that connects these myths to reality, the cosmic microwave background, CMB, a faint glow from the universe's infancy. This snapshot, etched 380,000 years after the Big Bang, offers clues to the cosmological boundary we seek, whispering of what might lie beyond the universe's edge. Let's explore this relic, letting its ancient light guide us like a beacon through the quiet night. This CMB is the afterglow of the Big Bang, a uniform hum of microwave radiation filling all of space, cooled to a mere 2.7 Kelvin above absolute zero. It marks the recombination epoch when the universe, once a searing plasma, cooled enough for protons and electrons to form neutral atoms, allowing light to travel freely. This light, stretched by the metric expansion we've discussed, is what we detect today as the CMB. Its discovery in 1965 by American physicists Arno Penzias and Robert Wilson working at Bell Labs in New Jersey was a serendipitous moment. They mistook the signal for radio noise until realizing its cosmic significance. Russian physicist Yakov Zeldovich had predicted such a signal building on earlier work by George Gamow confirming the Big Bang's reality. The CMB is a window to the universe's youth, a map of its earliest boundaries. This relic is more than a historical artifact. It's a tool for probing the cosmos. The CMB's anisotropies, tiny temperature variations like ripples in a cosmic pond, reveal the seeds of galaxies formed by quantum fluctuations stretched during cosmic inflation. Satellites like Europe's Planck mission, launched in 2009, mapped these variations with unprecedented precision, showing the universe's space-time topology is nearly flat, as we explored earlier. These measurements constrain the universe's size and shape, suggesting it may be infinite or finite but unbounded. If an edge exists, the CMB marks the farthest we can see the cosmic light horizon, beyond which light hasn't reached us. The question of what lies beyond, whether a void, a multiverse, or ontological nothingness, hinges on this ancient light. Cultures worldwide have sensed this primal glow in their creation stories. In ancient Egyptian mythology, the god Atum emerged from a dark void, his light birthing the cosmos, a narrative that parallels the CMB's emergence from the Big Bang's heat. In Aboriginal Australian Dreamtime stories, the sky's first light marks the creation of the world, a poetic echo of recombination. These tales, like the CMB, capture a moment when the universe transitioned from chaos to order. For you perhaps, gazing at a starry sky from a rooftop deck, this connection might feel intimate. The stars you see are part of the same cosmic story, their light, a distant cousin of the CMB's ancient glow, tying your quiet evening to the dawn of time. The CMB's influence extends to our lives. Its data informs missions like Japan's Light Bird probing cosmic inflation to test multiverse theories. Technologies like Wi-Fi, rooted in radio astronomy techniques developed for CMB studies, owe a debt to this science. The elements in your body, hydrogen, helium, forged in nuclear synthesis and shaped by dark energy's push, connect you to the CMB's era, when the universe first became transparent. As you rest tonight, the CMB becomes a quiet thread in our cosmic tale, a relic that illuminates the past and hints at the unseen, carrying our question, what lies beyond, into the gentle stillness of the night. In 1919, a British expedition led by astronomer Arthur Eddington sailed to the island of Principe, off Africa's west coast, aiming to test a revolutionary idea. During a solar eclipse, they measured starlight bending near the sun, confirming Albert Einstein's general relativity, a theory that redefined gravity as the curvature of space-time. This milestone, woven into our journey through the cosmic light horizon, the primordial singularity metric expansion, space-time topology, the observable universe, multiverse possibilities, ancient tales, ontological nothingness, quantum fluctuations, dark energy, and the cosmic microwave background, brings us to gravity's pivotal role. Gravity, the force that binds stars into galaxies and galaxies into clusters, shapes the universe's structure and its potential boundaries. As we seek what lies beyond the universe's edge, gravity offers a vital thread, a cosmic web that holds our story together. Let's trace its influence, letting it guide us like a steady hand through the stillness of the night. Gravity in Einstein's framework is not a force pulling objects together, but a warping of the space-time continuum, described by the Einstein field equations. Massive objects like stars or black holes curve space-time, causing nearby objects to follow these curves, much like marbles rolling toward a dip in a stretched sheet. In cosmology, gravity orchestrates the universe's evolution. After the Big Bang, it drove gravitational collapse, clumping matter into stars and galaxies, counteracting the accelerated expansion fueled by dark energy. The cosmic microwave backgrounds, anisotropies shaped by early gravitational effects, reveal this interplay. If the universe has an edge, gravity's influence might define it either by curving space into a finite closed form or balancing the infinite expanse of a flat cosmos. The history of gravity study spans cultures and eras. In the 17th century, English mathematician Isaac Newton described gravity as a universal force, but it was Einstein's 19R15 theory developed in Germany that revolutionized our view. Indian astrophysicist Subrahmanyan Chandrasekhar in the 1930s showed how gravity governs stellar evolution, predicting black holes where spacetime curves infinitely. By the 1990s, observations of gravitational lensing light bending around massive objects confirmed Einstein's predictions with contributions from Swiss astronomer Fritz Zwicky. These discoveries spanning continents show gravity's role in shaping the universe's structure from galaxy clusters to the space-time topology we've explored. If an edge exists, gravity might weave its boundary a limit defined by the interplay of mass and space. Cultures have long personified gravity's pull. In ancient Greek mythology, Gaia, the Earth Mother, anchors the cosmos, her weight a metaphor for gravity's embrace. In Yoruba, traditions from Nigeria, the deity Olorun holds the heavens, balancing creation's forces much like gravity balances dark energy's push. These stories, like the Shunyata of Buddhism or the Tao's flow, reflect humanity's sense of a force binding existence. For you, perhaps walking a familiar path under a starry sky gravity is a quiet companion, the weight of your steps, the orbit of the moon. It's a force that feels personal, connecting a moment of stillness to the cosmic web that holds galaxies together. Gravity's influence touches our lives. Missions like Europe's Gaia telescope map the Milky Way structure, revealing gravity's choreography. Technologies like satellite navigation, reliant on general relativity to correct for space-time curvature, owe a debt to this science. The elements in your body forged in the Big Bang and clustered by gravity tie you to this cosmic dance. As you rest tonight, gravity becomes a subtle thread in our story, weaving the universe's structure and hinting at its boundaries, a gentle force that cradles the cosmos and carries our question, what lies beyond, into the quiet expanse of the night. High in the Atacama Desert of Chile, where the air is so dry the stars seem to pulse with clarity, the Very Large Telescope hums with precision, its mirrors capturing light from galaxies billions of years away. This marvel of engineering, alongside others like NASA's James Webb Space Telescope, extends our gaze beyond the cosmic light horizon. The primordial singularity, the metric expansion, the space-time topology, the observable universe, multiverse theories, ancient cosmologies, ontological nothingness, quantum fluctuations, dark energy, the cosmic microwave background and the gravitational web. These tools, humanity's eyes on the cosmos, probe the cosmological boundary we seek, searching for clues to what lies beyond the universe's edge. Are these instruments glimpsing the limits of our reality, or merely scratching the surface of infinity? Let's explore their work, letting their light guide us like a beacon through the serene night. Telescopes like the James Webb Space Telescope JWST, launched in 2021, use infrared spectroscopy to peer through cosmic dust, capturing light from the universe's earliest galaxies. By studying redshift surveys, astronomers measure how metric expansion stretches light, revealing the universe's growth since the Big Bang. The JWST, a collaboration involving Canadian and European scientists, can detect objects near the cosmic light horizon, pushing our view closer to the recombination epoch. Meanwhile, Chile's Atacama Large Millimeter Array ALMA probes the cosmic microwave background's faint ripples, refining our understanding of space-time topology. These tools, enhanced by adaptive optics to correct atmospheric distortion, act like cosmic lenses, focusing on questions of whether the universe is finite, infinite, or part of a multiverse, and what lies beyond its unseen edge. The history of this quest is a global tapestry. In the 17th century, Italian astronomer Galileo Galilei turned his telescope skyward, revealing a cosmos far vaster than imagined. By the 20th century, Australian radio astronomer Ruby Payne Scott pioneered techniques that led to CMB detection, while Indian astrophysicist Jayant Narlikar contributed to theories of gravitational lensing, where light bends around massive objects revealing distant galaxies. These efforts, spanning continents, built the foundation for modern observatories like South Africa's Meerkat, which maps cosmic structures influenced by dark energy. Each telescope, from Galileo's crude lenses to ALMA's precision arrays, narrows the gap between us and the cosmological boundary, yet leaves the question of beyond tantalizingly open. Cultures have long used their own eyes to probe the cosmos. In ancient Mesopotamia, priests used star charts to divine cosmic order, imagining a boundary where gods dwelt. In Polynesian navigation, Pacific Islanders read the stars to cross vast oceans their sky, a map without edges echoing the multiverse's boundless realms. These traditions, like the Shunyata of Buddhism or the Norse Yggdrasil, reflect a universal urge to explore the unknown. For you perhaps lying under a blanket staring at Orion's belt, this urge might feel familiar, a quiet moment when the stars seem to whisper secrets connecting your gaze to humanity's timeless quest to see beyond. These technologies shape our lives. Observatories like Australia's Parkes Telescope inspire innovations in radio communication used in Wi-Fi and medical imaging. The gravitational lensing studied by Narlikar informs our understanding of the universe's mass-guiding missions like Europe's Euclid Telescope. The elements in your body, shaped by nucleosynthesis and gravitational collapse, link you to the stars these telescopes observe. As you rest tonight, the work of these cosmic eyes becomes a thread in our story, their light probing the vastness and carrying our question, what lies beyond, into the gentle quiet of the cosmos. In the heart of ancient Mexico, Aztec poets sang of a cosmos bounded by celestial serpents, their scales shimmering at the universe's edge, guarding realms beyond mortal sight. Across centuries, Japanese artist Hokusai etched the starry night into woodblock prints, capturing the heavens as a boundless dream. These mythopoeic visions, woven into our journey through the cosmic light horizon, the primordial singularity metric expansion, space-time topology, the observable universe multiverse possibilities, ancient cosmologies, ontological nothingness, quantum fluctuations, dark energy. The cosmic microwave background and the gravitational web reflect humanity's urge to imagine the cosmological boundary. As we probe what lies beyond the universe's edge, art, literature, and media become our guides, painting the unknown with human creativity. Let's explore this canvas, letting its colours flow like a gentle breeze through the night. Art has long served as a mirror to the cosmos. In the Renaissance Italian painter Giotto depicted a star-filled sky in his frescoes inspired by early astronomical observations, a precursor to Galileo's telescope sketches. By the 20th century, Dutch artist Vincent van Gogh's Starry Night swirled with cosmic energy, its spirals echoing the gravitational lensing we've studied. These works, blending observation and imagination, parallel scientific quests to map the observable universe. Modern films like Interstellar, directed by British filmmaker Christopher Nolan, draw on general relativity to envision wormholes, portals to realms beyond akin to the multiverse hypothesis. These creations, from paint to celluloid, give form to the question of what lies past the universe's edge, whether a void, a boundary, or another reality. The history of this interplay is global. In the 19th century, British poet Alfred Tennyson wrote of the deeps of space inspired by early telescopes, while Indian writer Rabindranath Tagore described the universe as a song without end, echoing metric expansion. The 1960s saw Soviet science fiction like the Strugatsky brothers' roadside picnic imagine alien realms, beyond our cosmos, paralleling cosmic inflation theories. These works, rooted in their era's science, show how imagination amplifies our understanding. The cosmic microwave background's discovery, for instance, inspired artists like Brazilian sculptor Lygia Clark, whose abstract forms mimicked the universe's early ripples, bridging art and cosmology in a shared quest for the unknown. Cultures worldwide have painted the cosmos's edge. In African sandrock art, stars mark a spiritual boundary, a threshold to other worlds, much like the cosmic light horizon. In Chinese mythology, the goddess Nuwa mends the sky's edges, a poetic echo of space-time topology. These archetypal narratives, like the Aztec serpents or Norse Yggdrasil, reflect humanity's need to envision the beyond. For you perhaps, flipping through a novel or watching a sci-fi film, this impulse might feel familiar, a moment when a story's vastness stirs wonder, connecting your quiet evening to the universe's grand canvas. Art's influence touches our lives. The redshift surveys conducted by telescopes like Australia's Square Kilometre Array inspire visualizations in planetarium shows, making cosmology accessible. Technologies like digital imaging used in both art and infrared spectroscopy owe a debt to this interplay. The elements in your body, shaped by nucleosynthesis and gravitational collapse, link you to the stars artists depict. As you rest tonight, the canvas of imagination becomes a thread in our cosmic story, painting the question what lies beyond with colours of wonder, inviting you to drift into the gentle vastness of the cosmos. As we reach the final chapter of our cosmic journey, let's pause to reflect on the path we've travelled, a tapestry woven from questions that have stirred humanity for millennia, what lies beyond the universe's edge. We began on a quiet porch, gazing at the cosmic light horizon, pondering the primordial singularity that birthed the cosmos, its metric expansion unfurling like a scroll, its space-time topology shaping its form. We explored the observable universe multiverse possibilities, ancient cosmologies, ontological nothingness, quantum fluctuations, the pulse of dark energy, the cosmic microwave background, the gravitational web, the telescopes probing the void, and the art that paints the unknown. Each thread has deepened our question, yet the answer remains elusive, a mystery that invites wonder rather than resolution. Where are you watching from, and what time is it in your corner of the cosmos? If this journey has soothed your mind, please give it a like, maybe subscribe, and let's keep exploring the stars together. Let's weave these threads together, letting the cosmos guide us into a gentle close. The universe born 13.8 billion years ago in the Big Bang is a story of creation and expansion. Its boundaries defined not by walls but by the limits of light and time. The cosmic light horizon, stretching 93 billion light-years across, marks what we can see, but beyond it the cosmos may continue infinite or curved as space-time topology suggests. The accelerated expansion driven by dark energy pushes this horizon ever farther, while gravitational collapse weaves galaxies into a cosmic web. The cosmic microwave background, a snapshot of the recombination epoch and quantum fluctuations at the Planck scale, hint at the universe's earliest moments, yet they don't resolve whether an edge exists. The multiverse hypothesis offers a vision of other realms, while ontological nothingness suggests a void beyond comprehension. These ideas, from Russian physicist Andrei Linde to Indian philosopher Nagarjuna, form a global tapestry of thought, each perspective a brushstroke on the universe's canvas. History has shaped this narrative. From Greek philosopher Anaximander's Apiron to British astronomer Arthur Eddington's confirmation of general relativity, from Australian radio astronomer Ruby Payne-Scott's contributions to Indian astrophysicist Jayant Narlikar's gravitational lensing, the quest to understand the cosmological boundary spans cultures and centuries. Telescopes like Chile's ALMA and Japan's LIGHTBIRD probing redshift surveys and anisotropies extend this legacy, seeking clues to whether the universe is finite, infinite, or part of a multiverse. These efforts, like the mythopoeic visions of Mesopotamian priests or Polynesian navigators, reflect humanity's drive to touch the infinite, a drive that resonates whether you're reading ancient texts or watching a starry sky. Cultures worldwide have enriched this story. The Aztec serpents guarding the cosmos's edge, the Chinese Tao as a formless source, the African sands starlit thresholds, and the Norse Yggdrasil linking realms all echo modern cosmology's questions. In literature, Indian poet Tagore's Boundless Song and Soviet sci-fi's Alien Realms mirror the multiverse and quantum veil. For you, perhaps curled up with a book or gazing at the Milky Way, these stories might stir a memory, a moment when a film like Interstellar or a painting like Van Gogh's Starry Night made the cosmos feel alive. The elements in your body, forged in nucleosynthesis and shaped by gravitational collapse, tie you to this narrative, making every breath a part of the universe's story. The question of what lies beyond remains open. Science offers no final answer, only possibilities. An infinite universe stretches without end, a flat topology with no edge. A finite one curves back, a closed topology with no beyond. A multiverse suggests other realms, while ontological nothingness offers silence. As you rest tonight, let this mystery be a gentle companion, not a puzzle to solve, but a story to hold like a familiar melody fading into quiet. The cosmos, with its galaxies, stars, and unseen realms, is a vast expanse that cradles your thoughts. Sleep well, and may your dreams drift among the stars. Welcome to Endless Universe, where the cosmos whispers its secrets to soothe your mind. I'm your sleep assistant, here to guide you through a gentle journey into the mysteries of the universe. Tonight we're drifting toward a question as timeless as the stars: how are galaxies and planets born? Imagine vast clouds of gas and dust swirling in the darkness, slowly knitting themselves into the glowing spirals of galaxies and the quiet spheres of planets. It's a story of creation, a cosmic lullaby written in stardust and sung across billions of years, inviting you to rest as you listen. Where are you watching from, and what time is it in your corner of the cosmos? Are you curled up under warm blankets with a cup of tea nearby, or perhaps gazing out at a starry sky from a quiet corner of the world? Let me know in the comments if you're still awake by the end. If this journey calms your mind or sparks a quiet wonder, I'd be ever so grateful if you gave this video a like, maybe tapped subscribe, and joined our little community of cosmic dreamers. It helps others find this tranquil corner of the universe where curiosity meets rest. Now, I hope this tale isn't so fascinating that it keeps you awake, but if it does well, at least you'll have learned something about the birth of everything before you drift off. Picture the universe as a vast quiet nursery not filled with cribs or blankets, but with gas dust and infinite possibility. Galaxies, those grand glittering cities of stars and planets, those humble worlds that spin silently in their orbits, all begin somewhere. But where? How does nothingness become something? How does the void give birth to the swirling arms of the Milky Way, or the rocky cradle of Earth? It's a process so slow, so patient, that it feels like the universe is taking its time, carefully crafting each star, each world, like an artist shaping clay under starlight. To understand this cosmic birth, we need to go back, way back to a time before galaxies, before planets, before even the stars themselves. The universe in its infancy was not a place of structure or form. It was a sea of energy, hot and chaotic, with no up, no down, just an endless expanse of potential. From this formless beginning, the seeds of galaxies were sown tiny ripples in the fabric of space that would grow into the vast structures we see today. Planets too have their origins in this cosmic dawn, but their story is more intimate, tied to the lives of stars and the dusty disks that swirl around them. It's a tale of gravity's gentle pull of particles finding each other in the dark of chaos, giving way to order. What does birth mean in the cosmic sense? On Earth, we think of birth as a moment, a spark, a breath, a beginning. But in the cosmos, birth is a process unfolding over eons, so gradual, it's almost imperceptible, like a dream taking shape in the quiet of night. Galaxies don't burst into being. They gather layer by layer as gravity weaves threads of gas and dust into tapestries of light. Planets don't simply appear. They coalesce grain by grain in the warm embrace of a star's gravity. It's a process that feels almost alive, as if the universe is breathing, expanding and creating with every moment that passes. This idea of cosmic creation has captivated humans for millennia. Ancient cultures looked to the skies and saw stories of gods and giants, weaving myths to explain the stars and worlds above. The Babylonians spoke of Marduk shaping the heavens. The Norse saw the cosmos as a great tree Yggdrasil holding worlds in its branches. The Aboriginal peoples of Australia told of the Dreamtime when ancestral beings shaped the land and sky. Even today, with our telescopes and equations, we're still chasing that same question: how does it all begin? Science gives us answers, but the wonder remains as timeless as the stars themselves. Let's linger on this idea of cosmic birth a little longer. It's not just the creation of something new, it's the transformation of what already exists. The universe doesn't start from nothing, it reshapes itself, recycling energy, matter and time into new forms. The hydrogen and helium that formed the first galaxies were born in the fiery crucible of the Big Bang. The dust that became planets was forged in the hearts of ancient stars. Everything in the cosmos is connected, a grand cycle of creation and rebirth that stretches across billions of years. This cycle is what makes the story of galaxies and planets so compelling. It's not just about distant objects in the sky, it's about us too. The elements in your body, carbon, oxygen, iron, were once part of stars that lived and died long before Earth was born. You are in a very real way a piece of the cosmos, a fragment of stardust that has journeyed through time to become you. And that's what we'll explore in this video, the slow, beautiful process that turns chaos into galaxies, dust into planets and the universe into a place where life can dream. Our journey will take us from the universe's first moments to the quiet formation of planets like our own. We'll wander through clouds where stars are born, disks where planets take shape, and the forces that sculpt galaxies into their majestic forms. It's a story that's both vast and intimate, distant and close to home, like looking at a starry sky and feeling it's part of you. So let's begin drifting into the cosmos, where galaxies and planets are born one quiet moment at a time. This is just the beginning, a gentle step into a story that spans billions of years and countless worlds. As we move forward, we'll unravel the science, the history and the poetry of cosmic creation. For now, rest easy, knowing that the universe is always building, always dreaming, always spinning new stories in the dark. You, dear traveller, are part of that story, a tiny spark in the endless universe, listening to its whispers as you drift towards sleep. To understand how galaxies and planets are born, we must travel back to the very beginning, to a moment when the universe itself took its first breath. Imagine a point smaller than a grain of sand, hotter than 1,000 suns, containing all the energy, matter, and possibility that would ever exist. This is the Big Bang, the cosmic spark that set everything in motion, the opening note of the universe's grand symphony. It's not an explosion in the way we think of fireworks or bursting balloons, but a rapid expansion, a stretching of space itself unfolding like a flower in the darkness, spreading light and potential across the void. This is where the story of galaxies and planets begins, in a moment so distant yet so close, for every star, every world, every breath you take traces back to this singular event. Let's picture the universe in its earliest moments, a sea of searing energy too hot for anything familiar to exist. There were no stars, no galaxies, no planets, just a plasma of energy and particles buzzing with unimaginable heat. The temperature was billions of degrees of furnace where even atoms couldn't hold together. Space itself was expanding, stretching like dough rising in a warm oven, carrying this primal soup farther and wider with every passing instant. In these first fractions of a second, the universe was a place of pure potential, a blank canvas waiting for the brushstrokes of creation. It's hard to imagine, isn't it? A time before time, a place before places, yet this is where the seeds of every galaxy and planet were sown. This early universe wasn't calm or orderly. It was chaotic, a swirling mix of particles and radiation with no structure to speak of. But something remarkable happened in those first moments, a process called cosmic inflation. Scientists believe that for a tiny sliver of time, less than a trillionth of a second, the universe expanded faster than light itself, ballooning from smaller than an atom to the size of a grapefruit, or perhaps larger in an instant. This rapid stretch smoothed out the universe, flattening its wrinkles like a sheet pulled tight across a bed, creating a near-uniform canvas of space. Yet within this smoothness, tiny imperfections remained like ripples on a quiet pond, and these ripples would become the blueprints for galaxies. These imperfections, known as quantum fluctuations, were minuscule variations in density, born from the uncertainty of the quantum world. Some regions of the early universe were ever so slightly denser than others, like patches of fog a bit thicker in a misty morning. Over time, gravity would tug at these denser spots, pulling matter together, setting the stage for the first structures to form. It's as if the universe planted tiny seeds in its own fabric seeds that would grow into the vast galaxies we see today, each one a glittering city of stars. These fluctuations were so small that they seem insignificant, yet they were the sparks that ignited the creation of everything we know. As the universe expanded and cooled, it began to take on a form we can start to recognize. Within the first second after the Big Bang, the searing plasma began to settle. Protons and neutrons formed, combining into the simplest elements, hydrogen and helium, the building blocks of stars. These elements were like the first ingredients in a cosmic recipe, simple but essential, ready to be cooked into galaxies and planets over billions of years. The universe was still too hot for atoms to fully form, but the foundations were there, floating in a vast cooling sea of light and matter. This early universe was bathed in light, a glow so intense it's hard to fathom. Photons, those tiny packets of energy, bounced endlessly between particles, creating a fog that made the cosmos opaque, like trying to see through a thick, radiant mist. For nearly 380,000 years, this fog persisted, until the universe cooled enough for electrons to join protons, forming neutral atoms. This moment, called recombination, was when the universe became transparent, like a curtain lifting to reveal the stage. Light was finally free to travel, and the photons from this era still drift through space today, forming the cosmic microwave background, a faint whisper of the Big Bang's first light. This cosmic microwave background is like a snapshot of the universe's infancy, a map of those tiny density fluctuations frozen in time. Scientists study it with telescopes, piecing together the story of how the universe began. Those denser patches, those seeds of creation, were where matter began to clump under gravity's gentle pull. Over millions of years, these clumps would grow, drawing in more gas and dust, forming the first stars and galaxies. It's a slow process, like watching a river carve a canyon, but it's relentless, driven by the quiet persistence of gravity. The Big Bang wasn't just the birth of the universe, it was the birth of possibility. The hydrogen and helium it created would become the raw materials for stars, which in turn would forge the elements needed for planets. The tiny ripples it left behind would shape the vast structures of galaxies, each one a cosmic tapestry woven from countless threads of light and matter. It's a story that feels almost personal, doesn't it? The atoms in your body, the carbon in your skin, the oxygen in your breath, all began in this fiery moment billions of years ago in a universe that was just learning to dream. This connection to the Big Bang makes the birth of galaxies and planets more than a scientific tale. It's a story of belonging. Every star in the sky, every planet orbiting a distant sun is a descendant of that first spark. And so, are you a tiny piece of the cosmos listening to its story as you drift in the quiet of night? The universe in its earliest moments was setting the stage for everything that would follow, from the swirling arms of the Milky Way to the gentle spin of Earth. It's a grand beginning, but a humble one too, built from the simplest ingredients and the softest ripples. As we drift further into this journey, we'll see how those ripples grew into clouds, how clouds became stars, and how stars gave birth to planets. For now, let's rest in the glow of that first moment when the universe was young, when everything was possible, and when the seeds of galaxies and planets were just beginning to take root. You're part of this story, a quiet spark in the endless universe, carried along by the same forces that shaped the cosmos, dreaming under the same ancient light. As the universe cooled and stretched after the Big Bang, its chaotic energy began to settle into something softer, more delicate. Imagine a vast dark canvas still warm from its fiery birth, now dotted with faint wisps of gas and dust, drifting like mist over a quiet lake. These wisps were the first molecular clouds, the cosmic nurseries where the seeds of galaxies and stars would take root. They weren't grand or glowing, not yet, but they held the promise of creation like a handful of clay waiting for an artist's touch. In these gentle clouds, the universe began to weave its first structures, setting the stage for the birth of galaxies, and eventually the planets that would orbit their stars. It's a story of patience, of quiet gathering, and of the universe learning to build. Picture these molecular clouds, vast and sprawling, stretching across light years, yet so thin you could hardly see them against the darkness. They were made mostly of hydrogen and helium, the simple elements born in the Big Bang's crucible, with traces of dust, tiny grains of carbon, silicon and ice forged in the hearts of the earlier stars that had already lived and died. These clouds weren't static. They moved swirling gently in the cosmic currents nudged by gravity and the faint ripples left from the universe's infancy. Some were small, destined to birth a single star, while others were enormous, holding enough material to form entire clusters, the building blocks of galaxies. These clouds were cold, far colder than anything we know on Earth, hovering just above absolute zero where warmth is but a memory. In this chill, molecules could form hydrogen atoms pairing up to create delicate bonds, cooling the gas further, making it denser and more ready to collapse. It's as if the universe was whispering to itself, coaxing these clouds into creation, like a gardener tending to fragile sprouts. This cooling was vital, for only in dense, cool clouds could gravity work its magic, pulling particles closer, tightening the threads of matter into knots that would one day ignite as stars. Gravity, that quiet architect, was the key to this transformation. In those denser patches where the Big Bang's ripples had left a little extra matter, gravity began to tug ever so gently, like a parent guiding a child's first steps. Over millions of years, these patches grew, drawing in more gas and dust, becoming denser, still like snowflakes piling into a snowball rolling down a hill. As they grew, the clouds began to fragment, breaking into smaller clumps, each a potential stellar nursery, a cradle where stars and later planets would be born. It's a slow dance, one that takes eons, but it's relentless, driven by the universe's deep desire to create. These stellar nurseries weren't empty or lifeless. They were alive, with motion, with energy, even in their cold silence. Within them, turbulence stirred the gas, creating swirls and eddies like cream mixing into a cup of tea. Magnetic fields threaded through the clouds, guiding the flow of particles, shaping their collapse. Sometimes shockwaves from nearby stars, those early giants that exploded as supernovae swept through, compressing the gas, sparking new collapses. It's as if the universe was playing a cosmic game of dominoes where one star's death could trigger the birth of many more. Let's linger in one of these nurseries for a moment, imagining a cloud so vast it could swallow our solar system 1,000 times over. Deep within a dense core forms a knot of gas and dust no larger than a city, yet heavy with potential. This core is the embryo of a star, a protostar glowing faintly with the heat of its own compression. Around it, the cloud continues to swirl a disk of leftover material that might one day become planets. This is where galaxies begin to take shape, not as single stars but as clusters, as families born together in these cosmic cradles. The birth of these first stars was a turning point for the universe. Before them, the cosmos was dark, a place of gas and silence, lit only by the faint glow of the cosmic microwave background. But when these stars ignited, fusing hydrogen into helium in their cores, they brought light to the darkness, like candles flickering in a vast empty room. These were no ordinary stars. They were massive, hundreds of times heavier than our sun, burning hot and fast, living only a few million years before exploding in brilliant supernova. Their death scattered new elements, carbon, oxygen, iron, into the surrounding clouds, enriching them for future generations of stars and planets. These early stars didn't form alone. In the densest clouds, hundreds or thousands ignited together, creating the first star clusters, the seeds of galaxies. Over time, these clusters merged, drawn together by gravity, forming larger structures. Irregular galaxies, small and chaotic, but the ancestors of the grand spirals and ellipticals we see today. It's as if the universe was sketching its first rough drafts, experimenting with shapes and sizes, learning how to build the cosmic cities we call galaxies. This process wasn't just about stars, it was about setting the stage for planets too. The disks of gas and dust around those early protostars were the precursors to planetary systems. Within them, tiny grains of dust began to stick together like snowflakes, forming in a winter storm, growing into the seeds of worlds. These disks were the universe's first workshops where the raw materials of planets, rock, ice, and gas began to take shape. It's a humbling thought, isn't it? The same clouds that birthed galaxies also held the potential for planets, for worlds where life might one day dream. The story of these molecular clouds is one of transformation, of turning the simple into the complex, the formless into the formed. They remind us that creation is a patient process, not a single moment, but a series of quiet steps, each building on the last. The hydrogen in those clouds, born in the Big Bang, would become the fuel for stars. The dust forged in stellar hearts would become the stuff of planets, and the galaxies they formed would become the homes for countless worlds, each one a tiny spark in the cosmic tapestry. As we drift through this story, let's carry the image of these clouds, vast and cold yet brimming with life. They're the universe's nurseries, where galaxies and planets begin, where chaos becomes order, and where the dark gives way to light. You too are part of this creation, made from the same stardust, listening to the same cosmic lullaby that began billions of years ago. Rest easy knowing that the universe is still weaving its clouds, still dreaming its stars, still crafting its worlds, one gentle swirl at a time. In the vast, quiet expanse of the early universe, where molecular clouds drifted like mist across a darkened sea, one force began to work its silent magic: gravity. Imagine gravity as a gentle hand reaching out across the cosmos, coaxing particles of gas and dust to come closer together, to weave themselves into something new. It's not a loud or forceful presence, not like the winds that sweep across Earth's plains, but a patient, persistent pull, as steady as a heartbeat. This force, so subtle yet so powerful, is the architect of galaxies and the sculptor of planets, turning the formless clouds of the universe's infancy into the glowing structures we see today. It's the story of how chaos becomes order, how the scattered becomes the whole, and how the universe builds its wonders, one gentle tug at a time. Let's picture those early molecular clouds, vast and cold, floating in the darkness like wisps of fog on a winter morning. Within them, the tiny density fluctuations from the Big Bang, those ripples in the cosmic fabric, created pockets where matter was just a little denser, like a slightly thicker patch of mist. Gravity, ever attentive, noticed these pockets and began its work. It pulled particles closer, not in a rush, but with a quiet insistence, like a parent gathering scattered toys into a neat pile. Over millions of years, these denser regions grew, attracting more gas, more dust, more of the universe's raw materials, until they became the seeds of something grander. This process wasn't uniform across the cosmos. In some regions, the clouds were massive, holding enough material to birth entire galaxies, collections of millions or billions of stars bound together by gravity's embrace. In others, smaller clumps formed, destined to become individual stars or clusters, each a potential cradle for planets. Gravity didn't discriminate. It worked the same everywhere, pulling matter together with the same steady rhythm, like a weaver threading a loom. The denser the clump, the stronger gravity's pull became, creating a feedback loop where more matter meant more attraction, and more attraction meant more matter, like a snowball rolling down a cosmic hill. As these clouds collapsed under gravity's influence, they didn't just shrink, they transformed. The gas and dust pressed closer, heating up as particles collided like the warmth you feel when you rub your hands together on a cold day. In the densest cores, this heat sparked the birth of stars, their fusion igniting like a candle in the dark. But gravity's role didn't end there. Around these newborn stars, the leftover gas and dust began to swirl, forming spinning disks like water circling a drain. These disks were the workshops where planets would later take shape, their materials gathered and sorted by gravity's patient hand. Gravity's influence extended beyond individual stars to the larger structures of galaxies. In the early universe, those initial density fluctuations grew into vast webs of matter, like a cosmic tapestry stretched across space. Scientists call this the cosmic web, a network of filaments, walls and voids where the densest regions became the birthplaces of galaxies. Imagine threads of light and matter crisscrossing the darkness, with galaxies forming at the intersections like dewdrops on a spider's web. Gravity pulled these threads together, shaping irregular clumps into the spirals, ellipticals and irregular galaxies we see today. This cosmic web wasn't just a backdrop. It was a dynamic system alive with motion. Galaxies collided and merged, their stars and gas mingling under gravity's guidance, like rivers joining to form a mightier stream. These mergers sculpted galaxies into their familiar shapes, with spiral arms curling like ribbons or elliptical galaxies glowing like soft rounded lanterns. Gravity was the artist, blending and reshaping, ensuring that no two galaxies were quite the same, yet all were bound by its universal rule. Let's not forget the planets, those smaller, more intimate creations. Within the disks around young stars, gravity continued its work, pulling dust grains together, one tiny collision at a time. These grains stuck, forming pebbles, then boulders, then planetesimals, the building blocks of planets. It's a process so delicate it's almost like the universe is knitting stitch by stitch, creating worlds from the simplest ingredients. Gravity ensured that these growing clumps stayed together, orbiting their stars, gathering more material until they became the rocky worlds or gas giants we know today. This gentle pull of gravity is something we experience every day, keeping our feet on the ground, holding our coffee in its cup. But in the cosmos, it's a force of creation, not just of holding things in place. It's the reason the moon orbits Earth, the reason our solar system spins in harmony, the reason galaxies cluster together in the vastness of space. It's like a cosmic glue binding the universe's pieces into a coherent whole, from the smallest dust grain to the largest galaxy cluster. The beauty of gravity lies in its simplicity. It doesn't need complex rules or flashy displays. It's a force that works the same whether it's pulling a leaf to the ground or a galaxy into being. Yet its effects are profound, shaping the universe over billions of years, turning the chaos of the Big Bang into the ordered structures we see today. It's a reminder that creation doesn't always need to be loud or sudden. Sometimes the most magnificent things are built slowly, quietly, with a gentle nudge that never gives up. As we drift through this story, let's hold on to the image of gravity as a cosmic gardener, tending to the universe's nurseries, coaxing clouds into stars, stars into galaxies, and dust into planets. You're part of this process too, made of atoms shaped by gravity's touch, living on a world it helped create. The same force that holds you to Earth once gathered the materials for its birth billions of years ago in a universe still learning to weave its dreams. Rest easy knowing that gravity is still at work, pulling, shaping, creating as the cosmos spins its endless tale. As gravity worked its quiet magic, pulling molecular clouds into denser clumps across the young universe, something extraordinary began to emerge. Picture a dark, vast canvas still cooling from the Big Bang's glow, now speckled with faint glimmers of light like fireflies waking in a twilight field. These were the first galaxies, fragile and small, nothing like the grand spirals or glowing ellipticals we know today. They were irregular, chaotic clusters of stars born in the densest pockets of the cosmic web where gravity had woven its earliest threads. These infant galaxies, often called dwarf galaxies, were the universe's first experiments in creation, humble beginnings that would grow into the cosmic cities we see in the night sky. Their birth marks a turning point when the universe began to shine, setting the stage for stars and planets to follow. Let's imagine the universe a few 100 million years after the Big Bang, still a young place barely 1 billion years old. The cosmic microwave background, that faint glow from the universe's infancy, still bathed everything in a soft light, but the darkness was giving way. In the densest regions of the cosmic web, where gravity had gathered vast clouds of hydrogen and helium, the first stars were igniting. These weren't solitary stars born alone in quiet corners. They formed in clusters, dozens or hundreds at a time, their light blending together like a chorus of candles in the dark. These clusters were the hearts of the first galaxies, small and irregular, like sketches the universe was still refining. These early galaxies were tiny by today's standards, often called dwarf galaxies, containing just a few million stars compared to the hundreds of billions in our Milky Way. They were messy, lacking the elegant spirals or smooth shapes of later galaxies, more like scattered handfuls of stardust than organized structures. Yet they were vibrant, filled with massive hot stars that burned brightly and died quickly, exploding as supernovae. These explosions scattered heavier elements, carbon, oxygen, nitrogen, into the surrounding gas, enriching it for future generations of stars and planets. It's as if these first galaxies were cosmic gardeners sowing seeds for the universe's next chapters. The stars in these galaxies were different from our Sun. They were giants, hundreds of times more massive, born from nearly pure hydrogen and helium, with almost no heavier elements. Scientists call them Population 3 stars, the first generation formed when the universe was still pristine. Their light was intense, their lives short, lasting only a few million years before collapsing in spectacular bursts. These explosions not only enriched the gas around them, but also sent shockwaves through the clouds, triggering new collapses, sparking more stars. It's like a cosmic chain reaction, where each star's death fueled the birth of others, weaving the galaxy tighter with every cycle. How do we know about these first galaxies so distant in time and space? Our telescopes, like time machines, peer into the past, capturing light that left these galaxies billions of years ago. The Hubble Space Telescope and the James Webb Space Telescope have glimpsed these faint ancient objects, their light stretched by the universe's expansion into the red end of the spectrum, a phenomenon called redshift. These observations show us galaxies as they were when the universe was young, small and irregular, glowing faintly against the cosmic dark. It's like looking at a photograph of the universe as a toddler, full of potential, but still finding its shape. These early galaxies didn't form in isolation. They were part of the cosmic web, that vast network of filaments and walls where matter clustered under gravity's pull. In the densest intersections, multiple star clusters merged, drawn together like friends gathering around a campfire. Over millions of years, these mergers built larger galaxies, some growing into the ancestors of the Milky Way. The process was slow, like dough, rising in a warm kitchen, but relentless, as gravity pulled more matter into the fold, creating structures that spanned tens of thousands of light years. The birth of these galaxies wasn't just a scientific event. It was a transformation of the cosmos itself. Before them, the universe was a dark, quiet place lit only by the fading glow of the Big Bang. These first galaxies brought light, structure and complexity like the first notes of a symphony that would grow richer with time. They were the universe's first attempt at organization, its first step toward creating the vast, interconnected tapestry we see today. And within these galaxies, the seeds of planets were already taking shape as the dust from dying stars began to gather in the disks around their successors. This story of creation feels distant, yet it's deeply personal. The elements forged in those early stars, carbon, oxygen, iron, are the same ones that make up your body, your breath, the ground beneath your feet. The first galaxies were the crucibles where these elements were born, scattered by supernovae to become part of new stars, new planets, new lives. It's a humbling thought, isn't it? That the light from those ancient galaxies still travelling across the cosmos connects you to the universe's earliest moments as you listen to this story under a starry sky. The birth of these galaxies also reminds us of the universe's patience. It didn't rush to create the Milky Way or Earth. It took its time, letting gravity gather, stars ignite, and galaxies merge over hundreds of millions of years. It's a process that feels almost serene, like a river carving a valley, steady and unhurried. Yet from this slow work came the vast structures that light up the night sky, the homes of countless stars and worlds, each one a testament to the universe's creative power. As we drift through this cosmic tale, let's hold on to the image of those first galaxies, small and chaotic, yet brimming with light. They were the universe's first steps toward becoming what it is today, a place of endless wonder where stars are born, planets form, and life can dream. You're part of this story, a spark of stardust from those early days, resting now in the quiet of night, carried by the same forces that shaped the cosmos. Let this thought soothe you as we journey deeper into the birth of galaxies and planets, one gentle moment at a time. With the first galaxies twinkling like scattered fireflies in the young universe, the cosmos began to find its rhythm. Those early irregular clumps of stars born in the dense knots of the cosmic web were just the beginning, like rough sketches on a vast canvas. Over billions of years, these fledgling galaxies would transform, sculpted by gravity collisions and the gentle churn of cosmic forces, into the majestic shapes we see today. Spirals swirling like cosmic pinwheels, ellipticals glowing like soft lanterns, and irregulars dancing to their own chaotic beat. Imagine the universe as an artist, refining its work, blending light and matter into forms that tell stories of creation, conflict, and beauty. This is the story of how galaxies take shape, a slow, graceful process that turns the universe's first sparks into the glowing cities of the night sky. Let's picture those early galaxies, small and disorderly, filled with massive stars that burned bright and died young. These dwarf galaxies, with their handfuls of stars, were like villages in the cosmic wilderness scattered across the expanding universe. They didn't stay isolated for long. Gravity, ever the matchmaker, pulled them toward one another like friends drawn together at a quiet gathering. When galaxies met, they didn't just pass by, they merged, their stars and gas mingling in a cosmic dance that could last millions of years. These mergers were the crucible where galaxies grew, transforming from small chaotic clusters into larger, more structured forms. The process of galaxy mergers is like a slow-motion waltz across the cosmos. Imagine two galaxies, each with its own stars, gas and dust, spiraling toward one another. As they draw closer, gravity stretches them, pulling out long tails of stars like ribbons trailing in a breeze. Their gas clouds collide, sparking bursts of star formation, lighting up the merging pair like fireworks in a silent sky. Over time, the two become one, their stars settling into new orbits, their gas pooling into new clouds ready to birth more stars. This is how galaxies grow, not just by gathering more matter, but by joining with others, blending their histories into something greater. These mergers gave rise to the diverse shapes we see today. Spiral galaxies like our Milky Way form when a galaxy's gas settles into a spinning disk, with arms curling like ripples in a pond. These arms are alive with star formation, glowing with the light of young hot stars, while older stars settle into a central bulge like a cozy village surrounded by vibrant fields. Elliptical galaxies, on the other hand, are smoother rounded like glowing orbs in the sky. They often form when multiple galaxies merge their stars, scattering into a more uniform shape like dough kneaded into a single loaf. Irregular galaxies, those that resist tidy forms, keep their chaotic charm, shaped by violent mergers or bursts of star formation that disrupt their structure. The Milky Way itself is a product of this cosmic sculpting. Billions of years ago, it began as a small irregular galaxy, one of many in the early universe. Over time, it merged with others, growing larger, its stars and gas settling into the spiral arms we see today. Even now, it's not finished. It's on a collision course with the Andromeda Galaxy, our nearest neighbour, in a merger that will unfold over billions of years, creating a new, larger galaxy. It's a reminder that galaxies are not static. They're alive, evolving, shaped by the universe's endless creativity. This shaping process wasn't just about gravity's pull. Other forces played a role, like the spin of galaxies inherited from the turbulence of their parent clouds. As galaxies formed, they spun their angular momentum, shaping their disks and arms, like a potter's wheel guiding clay into a bowl. Magnetic fields threaded through the gas, influencing how stars formed, while supernovae from dying stars sent shockwaves compressing gas and sparking new births. It's as if the universe was a symphony, with gravity conducting and stars, gas and dust playing their parts in harmony. These early galaxies were also shaped by their environment. In dense regions of the cosmic web where many galaxies clustered, mergers were frequent, creating massive ellipticals. In quieter regions, galaxies could grow more slowly, forming delicate spirals. The universe's structure, that web of filaments and voids, acted like a cosmic blueprint guiding where and how galaxies took shape. It's a beautiful thought, isn't it? That the universe's architecture laid down in the Big Bang still influences the forms of galaxies billions of years later. The birth and shaping of galaxies also set the stage for planets. Within these galaxies, stars formed in clusters, each surrounded by disks of gas and dust, the raw materials for planets. As galaxies grew and merged, they created richer environments, with more elements forged by dying stars ready to form rocky worlds and gas giants. The galaxies became the homes where planetary systems could thrive like neighborhoods, where families of stars and planets could settle. This story of galactic evolution has been pieced together by astronomers who study the light from distant galaxies to learn their histories. Telescopes like the James Webb Space Telescope capture images of galaxies as they were billions of years ago, showing us their chaotic youth. These observations reveal a universe in constant motion, where galaxies are not just born but reborn, reshaped by mergers and star formation, like a painting that's never quite finished. As we drift through this cosmic tale, let's hold on to the image of galaxies taking shape, their stars and gas swirling into forms that light up the night sky. They're more than just collections of stars, they're stories of creation, of collisions and connections, of chaos giving way to beauty. You're part of this story too, living in a galaxy shaped by billions of years of cosmic artistry, your atoms forged in the same stars that lit the universe's youth. Rest easy, knowing that the galaxies are still spinning, still merging, still crafting their shapes in the endless dance of the cosmos. As galaxies began to take shape, swirling into spirals and glowing as ellipticals, their hearts came alive with the birth of stars. Picture a galaxy as a vast glittering city, its streets lined with countless points of light, each one a star burning brightly in the cosmic night. These stars are more than just beacons. They are the universe's forges, where the simplest elements, hydrogen and helium, are transformed into the building blocks of planets and life. Inside their fiery cores, stars weave carbon, oxygen and iron, scattering these treasures across the cosmos when they die. It's a gentle, relentless process, like a blacksmith shaping metal, turning the raw materials of the Big Bang into the stuff of worlds. This is the story of how stars become the creators of everything we know, forging the elements that make planets possible. Let's drift into one of those stellar nurseries we visited earlier, a molecular cloud within a young galaxy swirling with gas and dust. Deep within, gravity has pulled a dense core together like a knot tightening in a rope. This core, a protostar, grows hotter as it collapses, its particles colliding and heating up, like embers glowing brighter in a campfire. When the temperature reaches millions of degrees, something miraculous happens. Nuclear fusion ignites, hydrogen atoms smash together, fusing into helium, releasing energy that pushes back against gravity's pull. The protostar becomes a true star, shining steadily a new light in the galaxy's tapestry. These stars, especially the massive ones born in the universe's early days, were the first cosmic forges. Unlike our sun, which burns slowly over billions of years, these early giants were hot and hungry, racing through their fuel in mere millions of years. Inside their cores, the pressure and heat were so intense that they didn't stop at helium. They fused helium into carbon-carbon into oxygen, and oxygen into heavier elements like neon, magnesium and silicon. Each step up the periodic table was like climbing a ladder, building more complex materials with every fusion reaction, like a chef adding new ingredients to a cosmic stew. The most massive stars went even further, forging elements all the way up to iron. But iron is where the forging stops. Unlike lighter elements, fusing iron doesn't release energy. It consumes it like trying to light a fire with wet wood. When a star's core fills with iron, its fusion engine stalls and gravity takes over, collapsing the star in a spectacular supernova. These explosions are among the universe's grandest events, outshining entire galaxies for a brief moment, scattering their forged elements, carbon, oxygen, iron, and more into the surrounding space. It's as if the star in its final act gifts its creations to the cosmos, like a painter flinging colours across a canvas. These scattered elements are the seeds of planets. The carbon and oxygen mix with the hydrogen and helium in molecular clouds, enriching them for the next generation of stars. When these newer stars form, they're surrounded by disks of gas and dust, now laced with heavier elements. These disks are where planets are born as dust grains stick together to form rocks, then boulders, then worlds. Without the work of those early stars, there would be no rocky planets like Earth, no oceans, no mountains, no life. Every atom of carbon in your body, every speck of iron in your blood was forged in the heart of a star that lived and died billions of years ago. Let's linger on this idea for a moment. The stars aren't just distant lights. They're the alchemists of the universe, turning the simple into the complex. Our sun, a modest star by cosmic standards, is part of this lineage, born from a cloud enriched by earlier supernova. Its planets, including Earth, are built from the ashes of those ancient stars, their elements gathered by gravity into the world we call home. It's like a cosmic family tree connecting you to stars that shone long before the sun was born, their light now faded, but their legacy enduring in every breath you take. This process of stellar forging wasn't a one-time event. It's ongoing, happening in galaxies across the universe. In the Orion Nebula, a stellar nursery visible from Earth, new stars are igniting, forging elements as we speak. Their supernovae will enrich the galaxy, further ensuring that future stars and planets have even more materials to work with. It's a cycle of creation where each star's death fuels new births, like a forest regrowing after a fire, each generation stronger and more diverse than the last. Astronomers have pieced together this story by studying the light from stars and the remnants of their explosions. Spectroscopy. The art of breaking light into its colours reveals the elements within stars, showing us the carbon, oxygen and iron they produce. When we look at supernovae, we see these elements scattered across space, their spectral fingerprints glowing in the debris. It's like reading a star's diary, each line revealing what it created in its lifetime, what it left behind for the universe to use. This forging process also shaped galaxies themselves. As stars formed and died, their supernovae sent shockwaves through the gas, triggering new star formation, helping galaxies grow denser and more structured. The elements they scattered enriched the galactic environment, making it possible for more complex systems, stars with planets with life to emerge. It's a beautiful thought, isn't it? That the stars in their fiery lives and explosive deaths are the universe's builders, creating the materials that make galaxies vibrant and planets possible. As we drift through this cosmic tale, let's hold on to the image of stars as forges their cores, glowing with the power to create. They're not just lights in the sky. They're the makers of worlds, the weavers of elements, the ancestors of every planet we know. You're part of this story too, a fragment of stardust forged in those ancient fires, living on a world shaped by their gifts. Rest easy, knowing that the stars are still burning, still forging, still scattering their treasures across the cosmos as the universe continues its endless work of creation. As stars ignite within the glowing nurseries of galaxies, their light casts a gentle glow on the next chapter of cosmic creation. Picture a young star newly born, surrounded by a swirling veil of gas and dust, spinning like a dancer's skirt caught in a soft breeze. This is the protoplanetary disk, a cosmic workshop where the raw materials of planets gather, twirl, and slowly come together. These disks are the cradles of worlds where tiny grains of dust begin a delicate dance that transforms them into rocky planets, gas giants, and everything in between. It's a process as graceful as it is profound, like a symphony played in silence across millions of years, turning the scattered remnants of star formation into the ordered orbits of planetary systems. This is the story of how planets begin to take shape, one gentle spin at a time. Let's drift closer to one of these young stars, its light still unsteady, like a candle flickering in a drafty room. As it forms, the star doesn't consume all the material in its parent cloud. Leftover gas and dust, enriched with elements like carbon and silicon from earlier supernovae, settle into a flattened disk around the star, held in place by gravity and spinning with the star's rotation. This protoplanetary disk is like a cosmic record spinning smoothly, its grooves filled with the potential for worlds. It stretches across millions of miles wider than the orbit of Neptune, yet it's thin like a sheet of paper stretched across a football field. Within this disk, the dance of planet formation begins. The gas, mostly hydrogen and helium, swirls alongside tiny dust grains, no larger than grains of sand or flakes of snow. These grains are the building blocks of planets made of silicates, carbon compounds, and ices forged in the hearts of ancient stars. As the disk spins, these grains collide, sticking together like snowflakes, forming a snowball growing into pebbles, then boulders over thousands of years. It's a slow, patient process, like a child building a sandcastle one grain at a time, each collision adding a little more to the growing clump. This clumping process, called accretion, is driven by gravity and the gentle nudge of collisions. The disk isn't a calm, orderly place, it's alive with motion, with eddies and swirls like cream stirring into coffee. These motions help dust grains find each other, their sticky surfaces bonding in the cold outer regions of the disk or melting together closer to the star's warmth. Over time, these clumps grow into planetesimals, objects the size of asteroids or small moons ranging from a few miles to hundreds of miles across. These are the seeds of planets, the first solid steps toward worlds like Earth or Jupiter. The protoplanetary disk is divided into regions, each shaping the kind of planets that form. Close to the star, where temperatures are high, only materials like metals and silicates can remain solid, forming rocky planets like Earth or Mars. These inner regions are like a cosmic forge where heat shapes sturdy, dense worlds. Farther out beyond what astronomers call the frost line, it's cold enough for ice's water, ammonia, methane to solidify. Here planetesimals can grow larger, gathering vast amounts of gas to become gas giants like Jupiter or Saturn, their massive forms dominating the outer disk like giants in a quiet village. The disk's dynamics are shaped by more than just gravity. The star's light and heat push lighter particles outward, while magnetic fields twist through the gas, guiding its flow like invisible threads. Sometimes turbulence stirs the disk, creating dense patches where planetesimals form faster like knots in a rope. Other times, the star's radiation clears gaps in the disk, carving paths where young planets begin to orbit like trails through a cosmic forest. It's a delicate balance where every swirl, every collision contributes to the creation of a planetary system. This process isn't unique to our solar system. Astronomers have observed protoplanetary disks around countless young stars, their shapes revealed by telescopes like ALMA, the Atacama Large Millimeter Array. These disks appear as glowing rings with gaps and spirals, hinting at planets already taking shape, like ripples in a pond showing where a stone has fallen. The star HL Tauri, just 1 million years old, has a disk with clear rings, suggesting planets forming in real time, a snapshot of creation frozen in light that travelled thousands of years to reach us. The beauty of protoplanetary disks lies in their universality. Across galaxies, wherever stars are born, these disks form each one a potential nursery for planets. Some disks birth systems like ours with rocky worlds and gas giants. Others create exotic worlds, super-Earths, mini-Neptunes, or planets orbiting twin stars like something out of a science fiction tale. It's as if the universe is experimenting, trying different recipes, crafting worlds as diverse as the galaxies that host them. This dance of disks connects us to the cosmos in a personal way. The Earth you stand on began in a disk like this, orbiting a young sun, its dust grains slowly gathering into the rocks and oceans we know today. Every mountain, every river, every breath you take traces back to those swirling clouds of gas and dust spinning in the quiet of space. It's a humbling thought, isn't it? That the worlds we call home were born in the gentle whirl of a cosmic disk, billions of years ago, in a galaxy still finding its shape. As we drift through this tale, let's hold on to the image of protoplanetary disks spinning gracefully around their stars, weaving planets from the simplest grains. They're the universe's workshops, where chaos becomes order, where dust becomes worlds, and where the cosmos dreams of life. You're part of this story too, a fragment of stardust shaped by the same forces living on a planet, born in a disk's embrace. Rest easy, knowing that the universe is still spinning its disk, still crafting its world, still dancing its endless dance of creation. Within the swirling protoplanetary disks around young stars, a quiet miracle unfolds, one so delicate, it's like the universe is holding its breath. Picture a disk of gas and dust spinning gently around a newborn star, its surface shimmering with countless tiny grains no larger than specks of sand. These grains, forged in the hearts of ancient stars, are the seeds of planets destined to grow from humble dust into the rocky worlds we call home. Through a slow, graceful process of collisions and clumping, these particles transform, gathering into planetesimals, and eventually planets like snowflakes, building into a snowball rolling across a cosmic field. This is the story of how dust becomes worlds, a tale of patience and persistence, weaving the simplest ingredients into the complex beauty of rocky planets. Let's drift into the heart of a protoplanetary disk where the star's light casts a warm glow on a sea of gas and dust. The disk is a busy place, alive with motion, like a river flowing in slow motion. The dust grains made of silicates, carbon and ices float alongside the hydrogen and helium gas carried by the disk's gentle spin. These grains are tiny, smaller than the particles in a puff of smoke, yet they hold the potential for entire worlds. As the disk orbits the star, the grains collide, their surfaces sticky from ice or static charge like lint clinging to a sweater, allowing them to bond and grow. This process, called accretion, is the first step in planet formation. The collisions are soft at first, happening at speeds slower than a bicycle's roll, but they're relentless, occurring over thousands of years. The grains grow into pebbles, then into boulders, each new size making them more likely to attract others, like a snowball gathering more snow as it rolls. Gravity begins to play a role even at these small scales, pulling larger clumps together, creating objects called planetesimals, rocky or icy bodies, ranging from a few miles to hundreds of miles across like asteroids or comets in our own solar system. These planetesimals are the building blocks of rocky planets, the universe's first attempt at crafting solid worlds. In the inner regions of the disk close to the star where temperatures are high, only materials like metals and silicates can remain solid. Here, planetesimals form from these heat-resistant ingredients growing into the cores of planets like Earth, Mars, or Venus. It's like a cosmic kitchen, where the star's heat bakes the ingredients shaping sturdy rocky worlds from the toughest materials. The process is slow, taking millions of years as planetesimals collide and merge their gravity, pulling in more debris like a magnet gathering iron filings. The formation of these rocky planets is a chaotic dance, not a neat assembly line. Planetesimals don't just drift together peacefully, they crash, sometimes shattering, sometimes sticking like clay being moulded by a sculptor's hands. These collisions release heat, melting parts of the growing bodies, allowing heavier materials like iron to sink to their cores, forming the layered structures we see in planets like Earth. It's a violent process, yet it's also creative, turning a jumble of rocks into a world with mountains, valleys, and the potential for oceans. In our own solar system, we see evidence of this chaotic youth. The Moon, for example, is thought to have formed when a Mars-sized planetesimal, often called Theia, slammed into the young Earth, flinging molten debris into orbit. This debris coalesced into the Moon, companion born from a cosmic accident now drifting silently beside us. Meteorites. Those ancient rocks that fall from the sky are also relics of planetesimals, their composition revealing the silicates and metals that shaped the early solar system. It's like holding a piece of the universe's childhood, a fragment from the time when dust was becoming worlds. Astronomers study this process by observing young star systems, where protoplanetary disks are still forming planets. Telescopes like ALMA capture images of these disks showing rings and gaps, where planetesimals are clearing paths like footprints in a snowy field. These observations confirm that the process is universal, happening across galaxies wherever stars are born. Each disk is a potential nursery crafting worlds, as unique as the stars they orbit, from rocky planets like ours to strange worlds we can only imagine. This journey from dust to worlds is a testament to the universe's ingenuity. It takes the simplest ingredients, grains of dust forged in long-dead stars, and transforms them into complex systems where planets spin in harmony around their suns. It's a process that feels almost alive, as if the universe is experimenting, trying new combinations, crafting worlds with care. The Earth we walk on, with its forests, rivers and skies, began as these tiny grains colliding in a disk billions of years ago in a galaxy still finding its shape. The story of rocky planet formation also connects us to the cosmos in a profound way. The elements in your body, carbon, calcium, phosphorus, were once dust grains in a protoplanetary disk, gathered by gravity, shaped by collisions, and baked into the planet you call home. You're a direct descendant of this process, a piece of stardust that found its way into a world listening now to the universe's quiet lullaby. It's a humbling thought, isn't it? That the worlds we inhabit, the lives we lead, began as specks of dust dancing in the light of a young star. As we drift through this cosmic tale, let's hold on to the image of those dust grains swirling in a protoplanetary disk, slowly building into worlds. They're the universe's smallest artists crafting planets, from the humblest beginnings, turning chaos into order and potential into reality. You're part of this story too, a spark of stardust shaped by the same gentle collisions, living on a world born from dust. Rest easy, knowing that the universe is still gathering its grains, still weaving its world, still dreaming its endless dreams of creation. As protoplanetary disks spin around their young stars, crafting rocky planets from dust and metal, another kind of world takes shape in the colder, outer reaches. Picture a vast, swirling disk, stretching far beyond the star's warm glow, where icy grains and gas gather like frost on a winter window. Here in these frigid realms, gas giants are born massive planets, like Jupiter and Saturn, cloaked in thick atmospheres, dominating their orbits like cosmic titans. These worlds, along with the moons, asteroids and comets that form from the disk's leftovers, complete the tapestry of a planetary system, turning a star's surroundings into a bustling neighborhood. It's a story of abundance and variety, where the universe uses every scrap of material, weaving grand planets and smaller remnants into a harmonious whole. Let's drift to the outer edges of a protoplanetary disk, where the star's light is faint and temperatures dip low enough for ice's water, ammonia, methane to solidify. In this chilly environment, planetesimals, those rocky and icy building blocks, grow larger than their inner disk cousins. The abundance of solid material like ice-covered grains allows them to accrete quickly, gathering mass like snowballs rolling through a blizzard. These growing cores become the seeds of gas giants massive enough to pull in vast amounts of hydrogen and helium from the surrounding disk, like a sponge soaking up water from a stream. The formation of a gas giant is a dramatic process. Once a planetesimal reaches a critical mass about 10 times that of Earth, its gravity becomes strong enough to attract gas directly from the disk. This gas, mostly hydrogen and helium left over from the Big Bang, flows onto the core, building a thick atmosphere that dwarfs the rocky planets closer to the star. Jupiter, for example, likely started as a rocky core perhaps the size of a small planet, before it began gulping gas, growing into the behemoth we see today with a diameter 11 times that of Earth. It's like a cosmic vacuum cleaner sweeping up material to become a giant in the sky. Saturn, with its stunning rings, followed a similar path, its core gathering ice and gas until it became a gas giant, its rings a remnant of the disk's debris that never formed a moon. These rings are like a cosmic keepsake, a reminder of the disk's chaotic youth sparkling in the starlight. Gas giants like these dominate their systems, their gravity shaping the orbits of other planets and debris like conductors leading an orchestra of celestial bodies. Their presence ensures that the disk's material is used efficiently, leaving little to waste. But not all material in the disk becomes planets. The leftovers dust rocks and ices that don't coalesce into larger bodies form a variety of smaller objects. Moons are one such creation, often forming in miniature disks around gas giants, like echoes of the larger protoplanetary disk. Jupiter's moon, Ganymede, larger than Mercury, likely formed from material orbiting the young Jupiter, accreting in a subdisk as the giant planet grew. These moons are like children of the gas giants born from the same processes, orbiting their parents in quiet harmony. Asteroids and comets are the disk's other leftovers, scattered across the system like crumbs on a cosmic tablecloth. Asteroids mostly rocky form in the inner disk, where temperatures are too high for ices like the asteroid belt between Mars and Jupiter in our solar system. Comets, with their icy cores and spectacular tails, originate in the outer disk where cold preserves their volatile materials. These objects are relics of the planet-forming process planetesimals that never grew large enough to become planets drifting in orbits that can last billions of years. The formation of gas giants and these leftovers is a testament to the universe's efficiency. Nothing goes to waste, every grain, every molecule finds a role, whether as a massive planet, a moon, or a wandering comet. In our solar system, we see this diversity in action: Jupiter and Saturn, with their thick atmospheres and retinues of moons, the asteroid belt a graveyard of planetesimals, and comets like Halley's, which swing by Earth every few decades, their tails glowing with released gases as they near the sun. It's like a cosmic scrapbook preserving the story of our system's birth. Astronomers study these processes by observing young star systems, where protoplanetary disks are still active. Telescopes like the Atacama Large Millimeter Array reveal disks with gaps carved by forming gas giants, their gravity sweeping clear paths like a broom through dust. These observations show us that gas giants form quickly within a few million years before the disk's gas dissipates, while smaller leftovers like asteroids and comets can linger longer, some surviving to the present day. It's a snapshot of creation captured in light that travelled thousands of years to reach us. This process connects us to the cosmos in a tangible way. The earth you walk on, the air you breathe, even the water in your glass all trace back to the materials in a protoplanetary disk. The gas giants with their massive presence helped shape our solar system, guiding smaller bodies into stable orbits, protecting Earth from excessive impacts. The asteroids and comets, those cosmic leftovers, sometimes fall to Earth, bringing clues about our origins like letters from a distant past. You're part of this story, a fragment of stardust that found its place in a system shaped by these grand and humble creations. The formation of gas giants and their leftovers is a reminder of the universe's creativity. It takes the same disk that crafts rocky worlds and spins it into giants' moons and wandering rocks, each with its own role in the cosmic dance. It's a process that feels almost poetic, as if the universe is weaving a tapestry, using every thread to create something beautiful. As we drift through this tale, let's hold on to the image of those swirling disks crafting worlds, from gas and dust building giants and scattering crumbs across the cosmos. Rest easy, knowing that the universe is still spinning its disks, still crafting its giants, still dreaming its endless dreams of creation. As we drift through the story of how galaxies and planets are born, let's turn our gaze to the humans who first looked up and wondered about the cosmos. Long before telescopes and equations, before we knew of protoplanetary disks or The Big Bang ancient cultures saw the night sky as a tapestry of stories woven with gods, heroes, and dreams. To them, the stars and planets weren't just distant lights. They were signs, guides, and mysteries sparking tales that shaped their understanding of creation. From the Mesopotamian plains to the Andean highlands, these early observers crafted myths about the birth of the heavens, their imaginations as boundless as the universe itself. This is the story of how ancient eyes saw the sky connecting us to the cosmic dance of galaxies and planets through the lens of human wonder. Imagine standing on a quiet hillside thousands of years ago, the sky above a glittering sea of stars unmarred by city lights. To the ancient Babylonians living in what is now Iraq around 2000 BCE, the stars were the work of Marduk, their creator god, who shaped the heavens after a cosmic battle. They saw the Milky Way, our galaxy, as a celestial river, its milky glow a path for divine beings. Planets which wandered against the fixed stars were messengers of the gods, their movements tracked with meticulous care. These early astronomers recorded the motions of Venus and Jupiter on clay tablets, not knowing they were planets born in a protoplanetary disk, but sensing their importance in the cosmic order. Across the world, the ancient Egyptians saw the sky as the body of Nut, the goddess of the heavens, her star-strewn form arching over the earth. They believed the sun and planets were born from her travelling across her body each night, a story echoing the real cosmic births we now study. In ancient China, astronomers like those of the Han Dynasty charted the stars, naming constellations and tracking planets, which they called wandering stars. They saw the cosmos as a harmonious system, its cycles reflecting the balance of life on Earth, a poetic parallel to the ordered orbits of planets around their stars. In the Americas, the Maya built observatories like the one at Chichen Itza to watch the sky with astonishing precision. They tracked Venus's cycles, linking them to myths of creation and rebirth, as if the planet's movements mirrored the universe's own birth from chaos. Their calendars, carved in stone, aligned with cosmic events, showing a deep understanding of the sky's rhythms, even without knowing the science of galaxy formation. The Aboriginal peoples of Australia told of the Dreamtime, a timeless era when ancestral beings shaped the land and sky, their stories painting the Milky Way as a river of spirits, a reflection of the galaxy's star-filled arms. These ancient perspectives weren't just myths. They were attempts to make sense of the cosmos, to find meaning in the lights above. The Greeks, for instance, saw planets as divine wanderers, naming them after gods like Hermes and Aphrodite, Mercury and Venus to us. Philosophers like Aristotle speculated about the heavens, imagining Earth at the centre of a universe filled with crystalline spheres, each carrying a planet or star. While their science was wrong, their curiosity was right, laying the groundwork for later astronomers who would unravel the true nature of galaxies and planets. Fast forward to the Renaissance, and figures like Nicholas Copernicus shifted our view. Copernicus proposed that the Sun, not Earth, was the centre of the solar system, a revolutionary idea that placed planets in orbits around a star, hinting at their formation in a disk. Galileo Galilei, with his telescope, observed Jupiter's moons, proving that not everything revolves around Earth, a step toward understanding planetary systems. These discoveries, built on ancient observations, brought us closer to the truth. Planets and stars are part of galaxies born from cosmic processes stretching back to the Big Bang. Even today, the stories we tell about the cosmos echo those ancient myths. In science fiction like Star Wars, galaxies are vast playgrounds filled with planets teeming with life, a modern take on the idea of a cosmos alive with meaning. The Voyager spacecraft, launched in 1977, carried a golden record with pulsar signals to mark Earth's place in the galaxy, a nod to ancient navigators who used stars to guide their way. It's as if we're still telling the same stories, but with new tools, telescopes instead of myths, equations instead of gods. These cultural perspectives connect us to the cosmos in a profound way. When you look at the night sky, you're sharing a moment with ancient stargazers who wondered just as you do about the origins of the stars and planets, the Milky Way. A faint band of light to them is now known to be our galaxy, born from mergers and star formation, yet it remains a source of wonder. The planets, once divine wanderers, are now worlds we study, their births traced to protoplanetary disks, yet they still inspire awe. This blend of ancient curiosity and modern science reminds us that the story of galaxies and planets is not just a tale of physics, it's a human story. The elements in your body forged in stars were seen by ancient eyes as divine sparks. The planets you dream of orbiting distant suns were once gods to those who watch the sky. You're part of this tradition, a stargazer in your own right, listening to the universe's lullaby as you drift towards sleep. As we journey through this cosmic tale, let's hold on to the image of those ancient skies filled with stories of creation. They remind us that galaxies and planets are more than matter. They're symbols of wonder, connecting us across time to the first humans who looked up and dreamed. Rest easy knowing that the cosmos is still telling its stories, still inspiring myths, still weaving its stars and worlds in the quiet of the night. You're part of this endless narrative, a spark of curiosity born under the same ancient sky. As we journey through the cosmic tale of how galaxies and planets are born, let's imagine turning our gaze upward, not with the naked eye, but through the lenses of humanity's greatest tools. Picture a telescope, its mirror gleaming like a quiet pond, capturing light that began its journey billions of years ago when the universe was young. Telescopes like Hubble and the James Webb Space Telescope are our windows into the past, letting us witness the birth of galaxies and the formation of planets as they happened eons ago. They transform the night sky into a cosmic archive where every photon tells a story of creation, from the first irregular galaxies to the swirling disks where worlds take shape. This is the story of how we peer through time, uncovering the universe's infancy, with each faint glimmer of light. Let's begin with the Hubble Space Telescope, launched in 1990, a marvel of human ingenuity orbiting high above Earth's atmosphere. Imagine it as a silent sentinel, its mirror gathering light from the farthest reaches of space, where galaxies glow as they did when the universe was just a fraction of its current age. Hubble's deep space images, like the famous Hubble Deep Field, reveal thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. These galaxies, some seen as they were just 1 billion years after the Big Bang, are small, irregular and chaotic, like cosmic toddlers still learning to walk. Their light, stretched by the universe's expansion, arrives, red-shifted a clue to their ancient origins, like a letter mailed long ago finally reaching its destination. Hubble's observations have shown us the universe's youth, a time when galaxies were forming in the dense knots of the cosmic web, their stars igniting in bursts of creation. These images capture the mergers that shaped early galaxies, their collisions sparking new stars like fireworks in a silent sky. Hubble also glimpses protoplanetary disks around young stars, their dusty rings hinting at planets in the making, like shadows of worlds yet to be born. It's as if Hubble is a cosmic historian piecing together the story of how galaxies and planets came to be, each snapshot a page in the universe's grand book. Now let's drift to the James Webb Space Telescope, launched in 2021, a newer, more powerful eye on the cosmos. Imagine Webb as a gentle giant, its golden mirror larger than Hubble's, designed to capture infrared light, the glow of objects too cool or distant for visible light. Infrared lets Webb peer through cosmic dust, like seeing through fog, revealing the hidden nurseries where stars and planets form. It also allows us to see even farther back to galaxies that existed just a few 100 million years after the Big Bang, when the universe was a mere infant. These galaxies, faint and irregular, are the ancestors of our Milky Way, their light travelling for over 13 billion years to reach us. Webb's images are like a time machine, showing us galaxies in their chaotic youth, merging and growing their stars, forging the elements that would later build planets. One of Webb's early discoveries was galaxies brighter and larger than expected at such early times, suggesting that galaxy formation began sooner and faster than we thought, like a garden blooming before spring. Webb also captures detailed views of protoplanetary disks, their rings and gaps carved by forming planets, offering clues about how worlds like Earth take shape. It's as if Webb is a cosmic detective, uncovering secrets hidden in the universe's earliest chapters. These telescopes don't just show us distant objects, they let us travel through time. Light takes years, centuries, or billions of years to reach us, so when we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago, not as it is today. This cosmic delay turns every telescope into a portal, letting us witness the universe's history unfold from the birth of the first galaxies to the formation of planetary systems. It's like flipping through an ancient photo album, each image capturing a moment in the cosmos's long journey. Beyond Hubble and Webb, other telescopes contribute to this story. The Atacama Large Millimeter Array, or ALMA, observes young star systems in our galaxy, its radio waves revealing protoplanetary disks in exquisite detail, like brushstrokes on a canvas. ALMA shows us planets forming in real time, their gravity sculpting rings and spirals in the dust, a process that mirrors the birth of our own solar system. Ground-based telescopes like those at Mauna Kea study the spectra of distant galaxies, revealing their composition and motion, like reading the fingerprints of creation. This scientific quest connects us to the ancient stargazers who looked up with wonder, though they had only their eyes and myths. Today we use mirrors and mathematics, but the curiosity is the same, driving us to ask how galaxies and planets are born. These telescopes are our modern campfires around which we gather to tell stories of the cosmos, each discovery a new tale of creation. The light they capture is a bridge between past and present, linking us to the universe's youth, when the first stars lit the dark and the first planets began to spin. This journey through time also reminds us of our place in the cosmos. The galaxies we see in Hubble's images, the disks in Webb's infrared glow, are part of the same universe that shaped our world. The elements in your body, forged in ancient stars, were part of those early galaxies scattered by supernovae to become planets like Earth. You're a fragment of that cosmic history, a spark of stardust carried through billions of years, listening now to the universe's quiet lullaby as you rest. As we drift through this cosmic tale, let's hold on to the image of those telescopes, their mirrors catching light from the universe's dawn. They're our guides showing us how galaxies and planets were born, revealing a cosmos alive with creation. Rest easy, knowing that the universe is still shining, still crafting its stories, still sending its ancient light to those who look up with wonder. You're part of this endless journey, a dreamer under the same cosmic sky, cradled by the light of stars born long ago. As we journey through the cosmic tale of how galaxies and planets are born, let's bring the story closer to home, to the familiar worlds that spin quietly around our sun. Picture our solar system, a cozy neighbourhood in the vast city of the Milky Way, where Earth, Mars, Jupiter and their siblings orbit in graceful harmony. These planets, born from the same processes that shaped distant galaxies and stars, are the result of dust and gas swirling in a protoplanetary disk billions of years ago. Their formation is a story of cosmic craftsmanship, turning scattered grains into the rocky landscapes and gaseous giants we know today. It's a tale that connects the grand sweep of the universe to the ground beneath your feet, making the birth of planets feel as intimate as a walk under the stars. Let's drift back about 4.6 billion years to a time when the Sun was a young star newly ignited in a molecular cloud within the Milky Way. Around it formed a protoplanetary disk, a spinning veil of gas and dust, rich with elements forged in ancient stars, carbon, oxygen, silicon and iron. This disk was like a cosmic workshop where the materials for our solar system gathered ready to be shaped. In its inner regions, where the sun's heat was fierce, dust grains of metal and silicates collided and stuck, forming planetesimals, the seeds of rocky planets like Earth, Venus, Mercury and Mars. It's as if the universe was baking a batch of sturdy worlds, using only the toughest ingredients that could withstand the sun's warmth. Earth's formation began with these planetesimal small rocky bodies crashing together in a chaotic dance. Over millions of years they merged, growing larger like pebbles piling into a mound. One monumental collision with a Mars-sized body called Theia reshaped Earth's early history. The impact flung molten debris into orbit, which coalesced into the Moon, a quiet companion that still lights our nights. This violent birth left Earth with a molten surface slowly cooling to form a crust like a cake setting in a cosmic oven. Over time, water vapor from the disk and comets condensed into oceans, turning our planet into a blue jewel capable of hosting life. Mars, our red neighbour, followed a similar path, its rocky surface forming from planetesimals in the inner disk. Smaller than Earth, it cooled faster, its volcanoes and canyons freezing. In time, like a snapshot of a young world's ambition, Venus, closer to the Sun, became a scorching twin to Earth, its thick atmosphere trapping heat, a reminder that a planet's fate depends on its place in the disk. Mercury, smallest and closest to the Sun, is a dense ball of metal forged in the hottest part of the disk, like a piece of iron left too close to the fire. Each rocky planet tells a unique story, shaped by the same processes but moulded by their distance from the Sun. Beyond the frost line, where the disk was cold enough for ices to form, gas giants like Jupiter and Saturn took shape. These giants began as rocky cores, growing massive enough to pull in vast amounts of hydrogen and helium, like sponges soaking up the disk's gas. Jupiter, the largest, became a cosmic titan, its gravity shaping the orbits of other planets and capturing dozens of moons like a king gathering a court. Saturn, with its iconic rings, formed similarly, Its rings a remnant of icy debris that never became a moon, sparkling like a cosmic crown in the sun's light. The outer solar system hosts the ice giants Uranus and Neptune, born in the disk's farthest reaches, where ices like methane and ammonia were abundant. These planets, smaller than their gas giant siblings, gathered less gas, but more ice. Their blue-green hues are testament to their chilly origins. Their moons and rings, like those of Jupiter and Saturn, formed from leftover material, orbiting in quiet synchrony, like dancers following a distant rhythm. The solar system's leftovers, asteroids, comets, and dwarf planets like Pluto are relics of this formation process. The asteroid belt between Mars and Jupiter is a graveyard of planetesimals that never became a planet, their orbits disrupted by Jupiter's massive gravity. Comets with their icy cores originate in the distant Kuiper belt and Oort cloud, swinging past the sun to display their glowing tails, like cosmic travelers sending postcards from their journeys. These objects are time capsules, preserving the dust and ice from the solar system's birth like keepsakes from a long-ago celebration. Astronomers study our solar system to understand planet formation across the universe. Meteorites, fragments of asteroids that fall to Earth, reveal the composition of the early disk, their minerals matching those in protoplanetary disks seen around other stars. Space missions like NASA's Voyager and New Horizons have explored our planets and their moons, showing us the diversity of worlds born from a single disk. It's like reading a family album, each planet a sibling with its own personality shaped by the same cosmic story. This story of our solar system connects us to the broader cosmos. The processes that formed Earth and its neighbours are the same ones crafting planets in distant galaxies, from the swirling disks to the collisions of dust. The carbon in your body, the water in your glass, the iron in your tools, all were born in a disk like the one that created our planets billions of years ago. You're a part of this cosmic neighbourhood, living on a world shaped by the universe's patient craftsmanship under a sky filled with stars that share the same story. As we drift through this cosmic tale, let's hold on to the image of our solar system, a family of planets born from a swirling disk, each one a unique creation. They remind us that the universe's story is our story too, connecting the ground beneath your feet to the stars above. Rest easy knowing that the cosmos is still crafting its worlds, still spinning its disks, still weaving its endless tale of creation. You're a spark in this story, a fragment of stardust dreaming under the same sky that birthed your world. As we near the end of our journey through the birth of galaxies and planets, let's linger on a profound truth. The universe is a master of renewal. Picture the cosmos as a vast recycling plant where nothing is truly lost, only transformed. Stars die in brilliant supernovae, scattering their elements to form new stars and planets. Galaxies merge their gas and dust, blending to spark fresh waves of creation. Planets too evolve their surfaces, reshaped by time, ready to become the seeds of future worlds. This cycle of birth, death, and rebirth weaves through the fabric of the universe, ensuring that every ending is a new beginning, like a river flowing from one valley to the next. It's a story of cosmic resilience, connecting the galaxies and planets we see today to the endless process of creation. Let's start with stars, the heart of this cosmic cycle. When a massive star reaches the end of its life, it doesn't fade quietly. It explodes as a supernova, a burst of light that can outshine an entire galaxy. Imagine a star, its core filled with iron, collapsing under gravity's weight, then rebounding in a shockwave that flings its outer layers into space. These layers carry the elements forged in the star's core: carbon, oxygen, nitrogen, and iron, spreading them across the galaxy like seeds scattered by a cosmic wind. These elements enrich molecular clouds, making them fertile for the next generation of stars and planets, like compost nourishing a garden. This enrichment is crucial for planet formation. The first stars born from pure hydrogen and helium had no rocky planets, as there were no heavier elements to form them. But their supernovae created the materials needed for worlds like Earth, with its mountains, oceans, and life. Each new generation of stars inherits this legacy, forming in clouds, laced with the ashes of their ancestors, their protoplanetary disks ready to craft planets. It's as if the universe is learning each cycle, building more complex systems from simple stars to worlds capable of hosting life. Galaxies too are part of this recycling process. They don't remain static. They evolve, merging with one another in cosmic dances that span billions of years. Picture two galaxies like the Milky Way and Andromeda spiraling toward each other, their gravity pulling stars and gas into long glowing tails. When they merge, their gas clouds collide, sparking bursts of star formation, like fireworks celebrating a new union. These mergers create larger, more complex galaxies, their structures reshaped into spirals, ellipticals, or irregular forms like clay molded by a sculptor's hands. The gas and dust from these mergers fuel new stellar nurseries, ensuring the galaxy's legacy continues. This galactic recycling isn't just about growth, it's about transformation. Some galaxies, after exhausting their gas, become quiescent, their star formation slowing, like a forest entering a quiet season. Others in dense clusters collide frequently, their mergers triggering waves of creation that ripple through the cosmic web. Even the supermassive black holes at galaxy centers play a role, their gravity pulling in gas that heats and glows, sometimes blasting jets that stir the surrounding material like a cosmic blender, mixing ingredients for new stars. It's a dynamic process where galaxies are both creators and creations, part of an endless cycle. Planets, though smaller, are also recycled. On Earth, tectonic plates shift grinding old crust into the mantle, while volcanoes spew new rock like a planet renewing its skin. Meteorites, remnants of the solar system's birth, fall to Earth, carrying materials that hint at our origins like letters from a distant past. In other systems, planets may be destroyed, their debris scattered into new disks ready to form second-generation worlds. It's as if the universe is a cosmic workshop, reusing every scrap to craft something new, from the smallest rock to the grandest galaxy. Astronomers observe this cycle across the universe. Telescopes like the James Webb Space Telescope capture galaxies in the act of merging their stars and gas blending to form new structures. ALMA reveals stellar nurseries enriched by supernovae, their dust glowing with the elements of dead stars. In our solar system, meteorites and comets show us the raw materials of planet formation, preserved for billions of years. These observations are like glimpses into a cosmic factory, where creation and destruction work hand in hand, each process feeding the next. This cycle connects us to the cosmos in a deeply personal way. The carbon in your body, the oxygen in your breath, the iron in your blood, all were recycled through stars that lived and died long before our sun was born. The Milky Way, our home galaxy, is itself a product of mergers, its spiral arm shaped by countless collisions. Earth, a rocky world born in a protoplanetary disk, is part of this cycle. Its surface constantly renewed its materials, tracing back to the universe's earliest moments. You're a living testament to this cosmic recycling, a spark of stardust carried through billions of years of creation. The beauty of this cycle lies in its continuity. The universe doesn't waste its materials, it reuses them, transforming endings into beginnings, like a story that never truly ends. Stars die to birth planets, galaxies merge to form new stars, and planets evolve to host new possibilities. It's a process that feels almost alive, as if the cosmos is breathing, dreaming, and creating with every turn of its cycle. It's a reminder that nothing is lost, only changed, and that every piece of the universe has a role in its endless tale. As we drift through this cosmic story, let's hold on to the image of the universe as a recycling plant weaving new creations from the ashes of the old. It's a place where galaxies and planets are born, die, and are born again, each cycle adding to the cosmos's beauty. Rest easy knowing that you're part of this endless renewal, a fragment of stardust shaped by the universe's tireless work, dreaming under a sky that's still crafting its next chapter. As we reach the end of our cosmic journey through the birth of galaxies and planets, let's pause to marvel at a simple, profound truth the universe is still creating. Picture the cosmos as a living tapestry, its threads of gas, dust, and light forever weaving new galaxies, new stars, new worlds. From the fiery spark of the Big Bang to the gentle spin of protoplanetary disks, the story of creation is not a tale of the past, but an ongoing symphony played across billions of years. Galaxies merge, stars ignite, and planets form in distant corners of the sky, each moment a new verse in the universe's endless song. This is the story of a universe still being born, a reflection on its ceaseless creativity, and a quiet invitation to rest in its wonder as you drift towards sleep. Let's imagine the cosmos today, 13.8 billion years after its birth, alive with activity. In the Orion Nebula, just a short cosmic hop from Earth, molecular clouds glow with the light of newborn stars, their protoplanetary disks spinning, crafting planets as we speak. Across the universe, galaxies collide, their gas-sparking waves of star formation, like ripples spreading across a starry pond. In distant clusters, the cosmic web still gathers, matter-forming galaxies that will shine for billions of years to come. It's as if the universe is a tireless artist never content to stop always adding new strokes to its canvas of light and matter. This ongoing creation is driven by the same forces we've explored: gravity's gentle pull, the fusion in stellar cores, the collisions in protoplanetary disks. In galaxies like our Milky Way, stars are born every year, their deaths as supernovae scattering elements that will form new worlds. The Andromeda Galaxy, our nearest neighbour, is hurtling toward us, set to merge in a few billion years, creating a new galaxy filled with fresh stars and planets. Even black holes, those silent giants at galaxy centres, play a role, their gravity-stirring gas to fuel star formation like a cosmic conductor guiding the orchestra. The planets forming today are as diverse as those in our solar system. Some are rocky worlds like Earth, cradling the potential for oceans and life. Others are gas giants like Jupiter, or strange exoplanets, super-Earths, mini-Neptunes, or worlds orbiting twin suns like something from a dreamer's tale. Astronomers using telescopes like the James Webb Space Telescope glimpse these forming worlds, their disks glowing in infrared, revealing the universe's creativity in real time. It's like watching a cosmic nursery where new planets are born, each one a unique creation, shaped by the same processes that built our home. This endless cycle of creation connects us to the cosmos in a profound way. The atoms in your body, carbon, oxygen, iron, were forged in stars that died long ago, their materials recycled into the Earth you walk on. The Milky Way, our galactic home, is still forming stars, still shaping its spiral arms, still part of the universe's ongoing work. You're a living piece of this cycle, a spark of stardust carried through billions of years, dreaming now under a sky that's still crafting its next chapter. It's a humbling thought, isn't it? That you're part of a universe that never stops creating, always spinning new stories in the dark. This story also reminds us of the universe's patience. Galaxies take billions of years to form planets, millions to coalesce, yet the cosmos never hurries. It builds slowly, deliberately, like a gardener tending to a vast field, knowing each seed will bloom in its time. This patience is a quiet comfort, a reminder that creation is a process, not a moment, and that every ending, every supernova, every galactic merger is a new beginning. It's a cycle that feels almost alive, as if the universe is breathing, dreaming, and creating with every turn of its cosmic wheel. As we reflect on this journey, we've wandered from the Big Bang's first spark to the swirling disks where planets form, from the chaotic youth of galaxies to the quiet spin of Earth. We've seen how gravity weaves clouds into stars, how stars forge elements, and how dust becomes worlds. We've peered through ancient myths and modern telescopes, finding wonder in the cosmos's endless creativity. Each step has brought us closer to the universe's heart, a place of constant renewal where galaxies and planets are born, die, and are born again. So where are you tonight, and what time is it in your corner of the cosmos? Are you curled up under warm blankets with the stars outside your window, or resting quietly in a far-off place, the night sky a distant glow? If this cosmic tale has soothed your mind or sparked a quiet wonder, I'd be ever so grateful if you gave it a like, maybe tapped subscribe, and shared this gentle journey with others. It helps our little community of dreamers grow, bringing more souls to this tranquil corner of the universe where curiosity meets rest. As we close this story, let's hold on to the image of a universe still being born, its galaxies spinning its planets, forming its stars, shining in the dark. You're part of this creation, a fragment of stardust shaped by the cosmos's endless work, dreaming under a sky that's always crafting something new. The universe is still weaving its tapestry, still singing its lullaby, still inviting you to rest in its wonder. Sleep well, dear traveller, and may your dreams drift among the stars, carried by the gentle rhythm of the cosmos forever in bloom.